On a quiet night in 1781, a musician in Bath, England, pointed a homemade telescope toward the sky and noticed something faint drifting where no one expected anything to be, a pale wanderer that had circled the sun for billions of years, unseen, until that very moment. This is a story that unfolds slowly, across a century and a half, through the patient work of astronomers who trusted mathematics over what their eyes could find, who predicted invisible worlds and then, against all odds, discovered them waiting in the dark. From William Herschel's accidental glimpse of Uranus, to the elegant calculations that revealed Neptune, to Clyde Tombaugh's long winter of searching for what would become Pluto, each discovery stretched the known boundaries of our solar system deeper into the cold and the quiet. If these gentle explorations help bring rest, perhaps consider subscribing for more nights like this one. And so the story begins. In the year 1780, if you had asked any learned astronomer in Europe to describe the solar system, they would have spoken with quiet confidence about a family of 6 worlds, 6 planets drifting through the darkness, bound to our sun by invisible threads of gravity. There was Mercury, small and swift, hugging close to the solar fires. There was Venus, brilliant and cloud-wrapped, the evening star beloved of poets. There was our own Earth, of course, with its faithful moon. Then came Mars, rust-colored and distant, followed by mighty Jupiter with its retinue of moons, and finally Saturn, encircled by those mysterious rings that Galileo had glimpsed but not understood, and that Huygens had later revealed to be a disk of matter surrounding the pale golden world. Beyond Saturn, astronomers believed, there was nothing but the fixed stars, scattered across the celestial sphere like seeds thrown by some cosmic hand. The solar system, in the minds of the 1780s, was complete, finite, and fully catalogued. This belief in a finished solar system was not merely tradition or assumption, though both played their part. It was supported by a curious mathematical relationship that had emerged in the 1760s and 70s, a numerical pattern that seemed almost too elegant to be coincidence. In 1766, a German astronomer named Johann Daniel Titius had noticed something peculiar about the distances of the planets from the Sun. If you took a particular sequence of numbers, beginning with 0, then 3, then doubling each subsequent term to get 6, 12, 24, 48, and 96, and if you added 4 to each of these numbers and then divided by 10, you arrived at values that corresponded remarkably well to the actual distances of the planets, measured in astronomical units, with 1 astronomical unit being the distance from the Earth to the Sun. Mercury sat at approximately 0.4 astronomical units, matching the formula beautifully. Venus resided at 0.7, the Earth at 1, Mars at 1.6, Jupiter at 5.2, and Saturn at roughly 10 astronomical units. The formula predicted these positions with surprising accuracy. Yet there was a gap, a curious absence in the sequence. The formula suggested that something ought to exist at 2.8 astronomical units from the Sun, in the vast space between Mars and Jupiter, but no planet occupied that position. Johann Elert Bode, another German astronomer, popularized this relationship in 1772, and it became known as the Titius-Bode law, though whether it deserved the name of law was debated even then. Some astronomers viewed it as a profound hint at the underlying architecture of creation, a mathematical fingerprint left by whatever force or intelligence had arranged the heavens. Others dismissed it as numerology, a pleasing coincidence without physical meaning. But the gap troubled many minds. Either the formula was merely approximate and therefore meaningless, or something existed at that distance that had not yet been found. The discovery of the asteroids, beginning with Ceres in 1801, would eventually fill this gap and seem to vindicate the Titius-Bode law, though that story lies beyond our present concern. For now, it is enough to note that in 1780, the formula predicted Saturn as the outermost planet, and beyond Saturn, the numbers offered no guidance, no expectation of further worlds. The telescopes of this era, the instruments through which astronomers peered at the heavens, had improved considerably since the days of Galileo and Kepler, though they remained modest by the standards of later centuries. Two fundamental designs competed for favor among observers. The refracting telescope, which used a lens at the front of a long tube to gather and focus light, had been the original form of the astronomical telescope, the kind that Galileo had turned toward Jupiter's moons in 1610. Refractors produced clear, sharp images, but they suffered from a persistent flaw called chromatic aberration, in which different colors of light bent by slightly different amounts as they passed through the glass, creating colored fringes around bright objects that blurred the view and frustrated precise observation. To minimize this effect, telescope makers built refractors with very long focal lengths, sometimes stretching the tube to 40 or 50 feet, making them unwieldy and difficult to point accurately at the sky. The reflecting telescope offered an alternative. Instead of a lens, it used a curved mirror at the bottom of the tube to gather light and bring it to focus, and because light reflected from a mirror does not separate into colors the way refracted light does, reflectors avoided the problem of chromatic aberration entirely. Isaac Newton himself had built one of the first practical reflecting telescopes in 1668, a compact instrument that demonstrated the principle elegantly. Yet reflectors had their own difficulties. The mirrors of this period were made not of glass but of speculum metal, an alloy of copper and tin that could be polished to a reasonable shine but tarnished quickly in the damp air of England and France, requiring frequent repolishing that gradually wore away the carefully figured surface. Speculum mirrors also absorbed a good deal of the light that fell upon them, making reflectors less efficient than refractors of equivalent size. Still, for observers who wished to build large light-gathering instruments without the expense and impracticality of enormously long refractor tubes, the reflecting telescope held considerable appeal. The great observatories of Europe in 1780 were centers of careful, systematic work, mapping the heavens and tracking the motions of known bodies rather than searching for new ones. At Greenwich, on the outskirts of London, the Royal Observatory had been established in 1675 by King Charles II, with the practical goal of improving navigation by providing accurate star positions and reliable tables of the Moon's motion. The post of Astronomer Royal carried considerable prestige, and in 1780, that position was held by Neville Maskelyne, a meticulous and somewhat austere figure who had occupied the role since 1765. Maskelyne devoted himself to the production of the Nautical Almanac, an annual publication of astronomical tables essential for sailors calculating their longitude at sea, and to the careful refinement of fundamental measurements. He was not a man given to speculation or to chasing faint glimmers in the darkness. His work was the patient accumulation of precise data, the slow improvement of numbers that mattered for practical purposes. Across the Channel, the Paris Observatory had been founded even earlier, in 1667, and had long been a rival to Greenwich in the production of star catalogues and the observation of celestial phenomena. The French astronomers pursued similar programs of careful measurement, and the two nations engaged in a gentle competition to produce the most accurate charts of the sky. Both observatories possessed capable instruments, trained observers, and the institutional continuity that allowed long-term projects to be carried through over decades, but neither was particularly oriented toward the discovery of new objects. The solar system, after all, was understood to be complete. The star catalogues upon which astronomers relied in this period were substantial achievements, though limited by the technology and observing conditions of their times. The most important English catalogue was the Historia Celestis Britannica, the posthumous work of John Flamsteed, the first Astronomer Royal. Flamsteed had spent decades at Greenwich, painstakingly measuring the positions of stars with his mural arc and transit instruments, and his catalogue, published in 1725 after his death, contained nearly 3,000 stars, each located with considerable precision by the standards of the era. It was an invaluable resource for astronomers who needed to identify stars, to check whether a faint point of light was a known object or something new, something that ought not to be there. Yet Flamsteed's catalogue, like all catalogues of fixed stars, was necessarily incomplete. The sky contains far more stars than 3,000, and vast regions remained unmapped or only roughly surveyed. An astronomer searching the heavens with a good telescope would frequently encounter stars that appeared in no catalogue, objects too faint or too far from the ecliptic to have attracted Flamsteed's attention, and this uncertainty created both opportunity and confusion. In the 1770s, a particular kind of celestial hunting had become fashionable among serious observers, a pursuit that combined patient watching with the thrill of discovery. Comets, those wandering visitors with their ghostly tails, appeared unpredictably in the sky, and the astronomer who first spotted a new comet and reported it to the scientific community earned recognition and acclaim. The calculation of cometary orbits had become a well-developed art following the work of Edmund Halley, who had famously predicted the return of the comet that now bears his name, and each new comet provided fresh data for testing and refining theories of celestial mechanics. But finding comets required distinguishing them from the countless faint, fuzzy patches of light that decorated the sky, the nebulae and star clusters that could easily be mistaken for approaching comets by an eager observer. No one understood this challenge better than Charles Messier, a French astronomer who had devoted his career to comet hunting with considerable success. Messier had discovered numerous comets and had earned a reputation as the foremost comet finder of his age, but he had grown weary of the false alarms, the evenings spent tracking a fuzzy object only to find that it remained stationary night after night, revealing itself as a fixed nebula rather than a moving comet. To spare himself and his fellow comet hunters this frustration, Messier began compiling a catalogue of these annoying nuisances, these objects that resembled comets but were not comets, so that observers could quickly eliminate them from consideration. The first version of his catalogue, published in 1774, contained 45 objects. By the end of the decade, it had grown to encompass many more. Messier cared nothing for these nebulae themselves, they were merely obstacles to his true purpose. Yet his catalogue would prove unexpectedly valuable, for it documented a population of deep sky objects that later astronomers would study intensively, and it habituated observers to the careful scrutiny of faint, fuzzy things, training eyes and minds in precisely the skills that would soon lead to unexpected discoveries. The broader intellectual context of this period, the mental atmosphere in which these astronomers worked and thought, was that of the Enlightenment, an age of confident rationality that believed the universe to be fundamentally orderly and comprehensible. The laws of Newton, published nearly a century earlier, had demonstrated that the motions of the heavens could be described by simple mathematical relationships, that the same force which pulled an apple to the ground also held the moon in its orbit and guided the planets along their elliptical paths. This success had encouraged a view of nature as a vast mechanism, intricate but ultimately knowable, a cosmic clockwork whose workings patient investigation could reveal. Philosophers and natural scientists of the 1780s generally expected that further study would continue to confirm and extend this orderly picture, that the universe would yield its secrets gradually to reason and observation without springing unpleasant surprises. This confidence extended to the solar system itself. The 6 known planets moved in predictable orbits, obeying Newton's laws with beautiful precision, and perturbation theory was being developed to account for the small deviations caused by mutual gravitational influences. The system seemed stable, balanced, and closed. There was no theoretical reason to expect additional planets, and the observational evidence appeared to support completeness. Saturn had been known since antiquity, visible to the naked eye as a slow-moving point of light among the stars, and nothing beyond it had ever been detected. The fixed stars were vastly distant, separated from the solar system by gulfs of space that no instrument could bridge, and the planets belonged to a finite, local family whose membership was established beyond reasonable doubt. Yet the very habits of careful observation that supported this confident picture also contained the seeds of its revision. The comet hunters sweeping the sky with their telescopes, the catalogue makers noting the positions of faint stars, the instrument makers grinding ever larger and more finely figured mirrors, all were creating conditions in which something unexpected might be noticed, in which a small anomaly could catch a trained eye and provoke investigation. The solar system was about to expand, not because anyone sought to expand it, but because a diligent observer, engaged in patient and seemingly unrelated work, would happen to notice that one faint point of light behaved differently from its neighbors, moving slowly against the background of fixed stars, revealing itself as something other than what it first appeared to be. But we need not hurry toward that moment. For now, we rest in 1780, in a world that believed itself to understand the bounds of the planetary family, in an age of orderly confidence and careful measurement, and we breathe gently as the slow night passes and the stars wheel overhead in their ancient, predictable courses. In the year 1738, in the German city of Hanover, a boy was born to a family of musicians, and he was given the name Friedrich Wilhelm Herschel, though the world would come to know him by the anglicized form of his name, William Herschel, and it was this man, decades later, who would become the first person in recorded history to discover a planet that had not been known to the ancient civilizations of Earth, a planet so distant and so faint that no one before him had ever recognized it for what it truly was. The Herschel family was not wealthy, but they possessed something perhaps more valuable in its own quiet way, which was a deep and abiding love of music, and young Friedrich Wilhelm grew up surrounded by the sounds of instruments and the patient teaching of his father, Isaac Herschel, who played the oboe in the Hanoverian Guards Band and who ensured that all of his children received thorough musical training from their earliest years. The boy learned to play the oboe and the violin, and he showed considerable talent, enough that he too joined the Hanoverian Guards Band as a young man, playing alongside his father and absorbing the disciplined rhythms of military music. But Hanover in those years was not a peaceful place, for the 7 Years' War brought conflict and upheaval to the region, and in 1757, following the Battle of Hasenbeck, the young musician found himself caught up in the chaos of a defeated army, and he made the decision that would reshape the entire course of his life, which was to leave his homeland and seek a new beginning across the sea in England. He arrived in England as a refugee of sorts, a young German musician with limited English and uncertain prospects, but he possessed determination and skill in equal measure, and slowly, patiently, he built a new life for himself in his adopted country. He taught music lessons, he copied sheet music for payment, he played in various orchestras and ensembles, and gradually his reputation as a capable and reliable musician began to grow. By 1766, he had secured a position as an organist in Halifax, and then, a few years later, he moved to the fashionable city of Bath, where he became the organist at the Octagon Chapel and established himself as a respected figure in the musical life of that elegant Georgian spa town. He composed symphonies and concertos, he conducted performances, he gave lessons to the sons and daughters of wealthy families, and by all outward appearances, he had achieved a comfortable and successful life as a professional musician in one of England's most pleasant cities. But there was another side to William Herschel, a side that had been growing quietly within him for years, nurtured by books and by an insatiable curiosity about the natural world. He had always been interested in mathematics and philosophy, in the grand questions about the nature of the universe, and sometime in the 1770s, this interest crystallized into a specific and consuming passion, which was the study of astronomy. He began to read everything he could find on the subject, working through the technical treatises and the observational catalogues, and he quickly realized that if he wished to see the heavens for himself, he would need a telescope, and not just any telescope, but one of considerable power and quality. The telescopes available for purchase in those days were expensive and often of disappointing quality, and Herschel, with his musician's income and his perfectionist tendencies, decided that he would simply make his own. This decision, which might seem modest enough in the telling, would lead him down a path of obsessive craftsmanship that bordered on the monomaniacal. He taught himself the art of grinding and polishing telescope mirrors, a process that required extraordinary patience and precision, for the metal mirrors of that era had to be shaped to exact mathematical curves and polished to a flawless shine. He would spend hours at a time grinding mirrors by hand, sometimes continuing for 16 hours without stopping, and his sister Caroline, who had joined him in Bath, would feed him by hand so that he would not have to pause in his work. The house at 19 New King Street became a workshop as much as a home, with mirrors and tools and half-finished instruments occupying every available space. Over the years that followed, William Herschel built more than 400 telescopes, each one an improvement on the last, each one reaching further into the depths of space. He experimented with different sizes and designs, with different alloys for his mirrors, with different methods of mounting and adjusting his instruments, and gradually he developed telescopes that were superior to almost anything else available in Europe at that time. His largest instruments were extraordinary achievements of amateur engineering, and even his smaller telescopes, the ones he used for his regular surveys of the night sky, were capable of revealing details that had eluded other observers. He was not content merely to build these instruments and admire them, of course, for he used them relentlessly, spending night after night in his garden or at the window of his house, systematically scanning the heavens and recording everything he saw. And so we come to the night of the 13th of March, 1781, a night that was cool and clear over the city of Bath, a night when the stars burned steadily in the darkness above the Georgian rooftops and the constellation of Gemini hung in the evening sky. William Herschel was at his telescope, a reflector with a mirror of 6.2 inches in diameter and a focal length of 7 feet. And he was engaged in one of his methodical surveys of the stars, moving his instrument slowly across a region of sky and noting the positions and appearances of every object he encountered. This was painstaking work, the kind of work that most people would find tedious beyond endurance, but Herschel approached it with the same disciplined patience that had served him well in his musical career, and he found a deep satisfaction in the slow accumulation of observations, in the gradual mapping of the celestial realm. Sometime between 10 and 11 o'clock that night, as he swept his telescope through the stars of Gemini, Herschel noticed something unusual, a small disk of light that did not look quite like the other stars in the field of view. The stars, when seen through a good telescope, appear as tiny points of light, sharp and unresolved, but this object appeared to have a discernible disk, a roundness that set it apart from its neighbors. Herschel noted the object carefully, recording its position and its appearance, and he suspected that he might have found a comet, for comets were known to show disk-like appearances in telescopes, and the discovery of a new comet was a noteworthy but not extraordinary event in the astronomical world of that era. In the nights that followed, Herschel returned to observe the object again and again, and he noticed that it was moving slowly against the background of fixed stars, which was consistent with his hypothesis that it might be a comet. He increased the magnification of his telescope from 227 times to 460 times and then to 932 times, and he found that the disk of the object grew larger with each increase in power, just as a planet or comet would, while the stars remained as points of light. On the 17th of March, he communicated his discovery to the Royal Society through a report to the Astronomer Royal, Neville Maskelyne, describing the object as a curious either nebulous star or perhaps a comet, and the astronomical community began to take notice. But as other observers turned their telescopes toward the object and began to track its motion through the sky, and as mathematicians began to calculate its orbit based on the accumulating observations, something unexpected emerged. The orbit of this object was not the elongated ellipse of a comet, swooping in from the outer reaches of the solar system and curving around the Sun before departing again. Instead, the orbit appeared to be nearly circular, and it lay far beyond the orbit of Saturn, at a distance from the Sun that was almost twice as great as Saturn's distance. The Finnish-Swedish mathematician Anders Johan Lexell, working in St. Petersburg, was among the first to recognize the implications of these calculations, and he concluded that the object discovered by Herschel was not a comet at all but rather a new planet, the first planet to be discovered in recorded human history, the first addition to the family of worlds that had been known since ancient times. The discovery caused a sensation in the scientific world and beyond, for it demonstrated that the solar system was larger and more populous than anyone had previously known, and it brought considerable fame to the music teacher from Bath who had built his own telescopes and swept the skies with such patient diligence. King George III, who took an interest in scientific matters, granted Herschel an annual stipend that allowed him to give up his musical career and devote himself entirely to astronomy, and in return, Herschel proposed that the new planet should be named Georgium Sidus, which is Latin for George's star, in honor of his royal patron. This proposed name, however, was not received with universal enthusiasm beyond the borders of Britain. French astronomers, who were not particularly inclined to honor a British monarch, suggested instead that the planet should be called Herschel, after its discoverer, and this name gained some currency on the continent. But neither Georgium Sidus nor Herschel satisfied the broader astronomical community, for there was a long tradition of naming the planets after the gods and goddesses of classical mythology, and many felt that the new planet should follow this convention. The German astronomer Johann Alertbode proposed the name Uranus, after the ancient Greek god of the sky, who was the father of Saturn in mythology just as Saturn was the father of Jupiter, and this name had the advantage of fitting neatly into the existing mythological scheme while avoiding the political complications of honoring either a living monarch or a living astronomer. The naming controversy dragged on for decades, with different names appearing in different publications and different countries, and it was not until around 1850 that the name Uranus became universally accepted, by which time Herschel himself had been dead for over a quarter of a century. But whatever name it bore, the planet remained as Herschel had first seen it, a pale greenish disk swimming in the darkness beyond Saturn, a world that had circled the Sun for billions of years without anyone on Earth knowing of its existence, until a German musician in an English garden turned his homemade telescope toward a particular patch of sky on a particular March evening and noticed something that did not look quite like a star. The discovery of Uranus was more than just the addition of a new world to the catalogues of astronomy, for it changed the way that people thought about the solar system and about the possibility of further discoveries. If one planet had lurked unseen beyond Saturn for all of human history, might there not be others, even more distant and even fainter, waiting to be found by observers with sufficient skill and patience and instruments of sufficient power? This question would occupy the minds of astronomers in the decades that followed, and it would lead, eventually, to discoveries that were even more remarkable in their own way, discoveries that relied not merely on keen observation but on the predictive power of mathematics and the gravitational interactions between unseen worlds. But all of that lay in the future on that March night in Bath, when William Herschel, the former military musician and current organist and indefatigable builder of telescopes, sat at his instrument and watched a tiny disk of light drift slowly among the stars of Gemini, not yet knowing that he had just expanded the boundaries of the known universe. The discovery of Uranus brought William Herschel something that few musicians turned amateur astronomers could ever have imagined, and that was the attention and patronage of a king. In the months following that March evening in 1781, as the astronomical community gradually accepted that this object was indeed a new planet, Herschel's name began to appear in correspondence between the learned societies of Europe, and his modest house on New King Street in Bath became a destination for curious visitors who wished to meet the man who had expanded the boundaries of the known solar system. Among those who took interest in this remarkable discovery was King George III himself, who had long held a genuine fascination with science and who maintained his own astronomical observatory at the royal residence in Kew. The king invited Herschel to bring one of his telescopes to court so that the royal family might observe the heavens through the same instrument that had revealed this distant world, and Herschel obliged with characteristic thoroughness, transporting his equipment and demonstrating its capabilities to an appreciative audience of nobles and courtiers. The relationship between the Hanoverian king and the Hanoverian musician proved to be a fortuitous one, grounded in mutual respect and a shared appreciation for the systematic observation of nature. George III, recognizing that Herschel's talents were being divided between the demands of musical performance and the calling of astronomical research, offered a solution that would change the course of Herschel's life entirely. The king proposed to grant Herschel an annual stipend of £200, a sum that was modest by the standards of royal patronage but sufficient to allow Herschel to abandon his musical career and devote himself fully to the study of the heavens. In exchange, Herschel would serve as the king's personal astronomer, making his telescopes available for royal viewing whenever requested, and continuing his surveys of the sky from a location conveniently close to Windsor Castle. This arrangement, formalized in 1782, transformed William Herschel from a provincial music teacher who happened to make telescopes into something approaching what we might now call a professional scientist, though that term itself would not come into common usage for another half-century. The move from Bath to the vicinity of Windsor required Herschel to uproot the life he had built over more than 2 decades, but the opportunity to pursue astronomy without the constant interruption of concerts and music lessons was too valuable to refuse. He settled first in the village of Thatchet, where the damp conditions near the Thames proved troublesome for both his health and his instruments, and then moved to a more suitable property in the town of Slough, where he would remain for the rest of his life. The house at Slough, known as Observatory House, became both his residence and his workplace, with the gardens serving as the site for increasingly ambitious telescope construction. Caroline Herschel, who had shared her brother's home in Bath and had become indispensable to his astronomical work, made the journey with him, continuing her role as assistant, recorder of observations, and manager of the household affairs that might otherwise have distracted William from his research. With the security of royal patronage and the freedom from musical obligations, Herschel began to contemplate the construction of a telescope far larger than any he had previously attempted. The instruments that had served him so well in Bath, including the 7-foot reflector with which he had discovered Uranus, were remarkable achievements of craftsmanship, But Herschel understood that larger mirrors could gather more light and reveal fainter objects in the depths of space. He began work on what would become the most famous telescope of the 18th century, an enormous instrument with a mirror measuring 4 feet in diameter and a tube extending 40 feet in length. The king himself provided additional funding for this ambitious project, contributing a grant of £2,000 toward its construction and later adding further sums as the costs inevitably exceeded initial estimates. The telescope took several years to complete, with the mirror requiring repeated casting attempts before a satisfactory result was achieved, and the supporting framework demanding engineering solutions that pushed the boundaries of what was then possible. The great 40-foot telescope was finally completed in 1789, and it stood in the gardens of Observatory House as an imposing monument to Herschel's determination and the king's generosity. The structure required a complex system of ladders, platforms, and pulleys to operate, and the observer was obliged to climb to a precarious perch near the mouth of the tube, exposed to the elements and reliant on assistants below to adjust the telescope's position according to shouted instructions. The mirror itself was made of speculum metal, that same alloy of copper and tin that Herschel had mastered in his Bath workshop, and its great size meant that it was extraordinarily heavy, difficult to polish to the necessary precision, and prone to tarnishing in the damp English air. In truth, the 40-foot telescope proved to be less useful than Herschel had hoped, its unwieldiness making systematic observation difficult, and its optical quality never quite matching that of his smaller, more carefully figured instruments. The sheer size of the mirror meant that any imperfections were magnified, and the challenges of supporting such a heavy piece of metal without distortion were considerable. Herschel found himself returning frequently to his 20-foot telescope, which offered a more practical compromise between light-gathering power and ease of use, and the great 40-foot instrument became as much a symbol of astronomical ambition as a working scientific tool. Despite its limitations, the 40-foot telescope did provide Herschel with one notable success on the very night of its first serious use, when he observed the sixth moon of Saturn, a small body that would later receive the name Enceladus. This discovery, made on the 17th of August 1789, demonstrated that even the difficult 40-foot instrument could reveal objects too faint for smaller telescopes, though Herschel would make most of his subsequent discoveries with more manageable equipment. Just weeks later, using the same great telescope, he identified another of Saturn's moons, the seventh to be found, which was given the name Mimas in accordance with the mythological naming convention that had been established for the satellites of that ringed planet. These discoveries added to a remarkable catalogue of new objects that Herschel had been accumulating since his identification of Uranus, and they reinforced his reputation as the foremost observational astronomer of his age. The moons of Uranus itself did not escape Herschel's attention, and 2 years before the completion of his 40-foot telescope, using the 20-foot reflector that remained his most reliable instrument, he had detected 2 satellites orbiting the planet he had discovered. On the 11th of January 1787, Herschel observed 2 faint points of light moving in company with Uranus, maintaining fixed positions relative to the planet as it drifted slowly against the background stars, and he correctly identified these as moons rather than distant background objects. These satellites, far smaller and fainter than the 4 great moons of Jupiter or the principal satellites of Saturn, would eventually be named Titania and Oberon, following a suggestion made by Herschel's son John, who chose names not from classical mythology but from the fairy kingdom of Shakespeare's A Midsummer Night's Dream. The naming was appropriate in its way, for these dim attendants of Uranus seemed to belong to a realm beyond the familiar, orbiting a world that lay at the very edge of visibility and moving according to laws that confirmed the gravitational theories of Newton. Through all of these discoveries and throughout the years of intensive observation, Caroline Herschel remained her brother's constant collaborator, and her contributions to astronomy extended well beyond the supportive role of assistant. She had learned to observe systematically, to record data precisely, and to perform the mathematical calculations necessary to reduce raw observations to meaningful positions and motions. When William was engaged with telescope construction or occupied with other matters, Caroline would observe independently, sweeping the sky with a small reflector that her brother had built specifically for her use. Her diligence was rewarded with discoveries of her own, most notably a series of 8 comets that she identified between 1786 and 1797, making her one of the most successful comet hunters of the era. The first of these comets, found in August 1786, was the first comet ever discovered by a woman, a distinction that brought Caroline recognition from the astronomical community and eventually a modest pension from the king in acknowledgement of her services to science. She also undertook the laborious task of organizing and indexing the observations that she and William had accumulated, producing catalogues that would prove invaluable to later astronomers and earning her a gold medal from the Royal Astronomical Society, the first ever awarded to a woman. In the final years of the 18th century, Herschel's curiosity led him beyond the visible light that had been the sole province of astronomical observation since antiquity. In 1800, while investigating the heating effects of different colors of sunlight, he made a discovery that would have profound implications for the future of physics and astronomy alike. Using a prism to spread sunlight into its component colors and placing thermometers at various positions within the spectrum, Herschel noticed that the thermometer positioned just beyond the red end of the visible spectrum, in a region where no light appeared to fall, registered the highest temperature of all. He had discovered what he termed calorific rays, radiation that could transmit heat but which was invisible to the human eye, and which we now know as infrared radiation. This finding revealed that the spectrum of light extended beyond what human vision could perceive, opening the possibility that the universe might contain forms of radiation entirely unknown to observers limited to their unaided senses. Though Herschel did not pursue the implications of this discovery extensively, it planted a seed that would grow into the rich field of spectroscopy and eventually transform our understanding of the composition and nature of celestial objects. The broader impact of Uranus's discovery on the astronomical community was considerable, and it prompted a general reassessment of assumptions that had gone largely unquestioned for centuries. If a planet had been orbiting in the outer reaches of the solar system, unrecognized despite being occasionally visible to the naked eye and recorded multiple times in star catalogues, then what else might be waiting to be found by diligent observers with sufficiently powerful instruments? Herschel had demonstrated the value of systematic surveys, of examining every portion of the sky with careful attention rather than focusing exclusively on the planets, stars, and nebulae that were already known. His catalogues of double stars, star clusters, and nebulae grew to include thousands of objects, far exceeding anything previously compiled, and his methods inspired a generation of astronomers to undertake similar programs of comprehensive observation. The solar system, which had seemed complete and well understood since Copernicus placed the Sun at its center, was revealed to be potentially larger and more populous than anyone had supposed, and the question of whether still more planets might exist beyond Uranus became a subject of legitimate scientific inquiry. As the years passed and observations of Uranus accumulated, astronomers began to notice something troubling about the new planet's motion. The orbit that had been calculated for Uranus, based on Newton's laws of gravity and the known positions of the Sun and the other planets, did not quite match the positions where Uranus was actually observed. The discrepancies were small, mere seconds of arc that would have been undetectable with the instruments of an earlier age, but they were persistent and they followed a pattern that could not be easily dismissed as observational error. Some astronomers suggested that Newton's law of gravitation might not apply precisely at such great distances from the Sun, a troubling possibility that would have undermined the foundations of celestial mechanics. Others proposed that the old observations of Uranus, those made before Herschel's discovery when the object had been recorded as a star, might be unreliable and should be disregarded. But a third possibility gradually gained adherents: the idea that Uranus was being pulled slightly off course by the gravitational attraction of yet another planet, one even more distant and as yet undiscovered. This hypothesis, which would eventually lead to the prediction and discovery of Neptune, represented the next chapter in the exploration of the outer solar system, and it demonstrated that the finding of Uranus had been not an ending but a beginning, opening questions that would occupy astronomers for decades to come. In the years that followed William Herschel's discovery of Uranus, astronomers set about the careful and patient work of tracking this new world as it moved through its orbit around the Sun. This was, in many ways, the quiet and methodical labor that forms the backbone of astronomy, the sort of work that rarely captures the public imagination but which slowly builds the foundation upon which all our understanding rests. Night after night, observers at various locations around the world noted the position of Uranus against the background stars, recording tiny angles and making small adjustments for atmospheric refraction and the wobble of the Earth's axis, all in service of mapping out the precise path this distant planet followed through space. And for a time, everything seemed to proceed in an orderly fashion, with Uranus behaving more or less as the mathematics of celestial mechanics predicted it should. But as the decades passed, a peculiar difficulty began to emerge, slowly at first, like a faint discordance in an otherwise harmonious piece of music. The observed positions of Uranus were not quite matching the positions that had been calculated in advance. The differences were small, certainly, measured in those tiny angular units that astronomers use, but they were persistent, and they were growing. And so began one of the most fascinating puzzles in the history of planetary astronomy, a puzzle that would occupy some of the finest mathematical minds of the 19th century and would ultimately lead to one of the most remarkable predictions ever made about the contents of our solar system. But we are getting ahead of ourselves, and for now, let us simply settle into this story of accumulating discrepancy and patient investigation. To understand the nature of this problem, we must first appreciate how astronomers go about predicting where a planet will be at any given time. The fundamental framework for this work was established by Isaac Newton in the late 17th century, when he showed that the same force of gravity that causes an apple to fall from a tree also governs the motion of the planets around the Sun. From Newton's laws of motion and his law of universal gravitation, mathematicians could derive equations that described elliptical orbits, and if they knew the position and velocity of a planet at one moment in time, they could calculate where it would be at any future moment. In practice, this calculation was complicated by the fact that each planet feels not only the gravitational pull of the Sun but also smaller tugs from all the other planets, and accounting for these perturbations, as they are called, required elaborate and painstaking mathematical analysis. The French astronomer and mathematician Alexis Bouvard undertook precisely this kind of work for Uranus in the early 19th century. Bouvard was a meticulous calculator who had previously compiled tables for the motions of Jupiter and Saturn, and in 1821 he published his tables for Uranus, which were intended to allow astronomers to predict the planet's position for many years into the future. In constructing these tables, Bouvard had access to two distinct sets of observations. The first set consisted of the numerous observations made since Herschel's discovery in 1781, which by 1821 amounted to about 40 years of careful tracking. The second set was rather more surprising, for it turned out that Uranus had actually been observed several times before Herschel realized it was a planet, by astronomers who had recorded it as a faint star. The earliest of these pre-discovery sightings was made by John Flamsteed, the first Astronomer Royal of England, who observed Uranus on at least one occasion in December of 1690. Nearly a century before Herschel's telescope revealed its true nature. Flamsteed had recorded the object as a star in the constellation Taurus, noting its position with his customary care but having no reason to suspect it was anything other than a fixed point of light in the heavens. Even more extensive were the observations made by the French astronomer Pierre-Charles Lemonnier, who recorded Uranus no fewer than 12 times between 1750 and 1769, over a span of nearly 20 years. Lemonnier, too, had catalogued these sightings as stellar observations, never noticing that the object had moved slightly between his various records. It is said, though perhaps apocryphally, that if Lemonnier had been more systematic in organizing his notes, he might well have discovered the motion of Uranus himself and claimed the honor that eventually fell to Herschel. These pre-discovery observations were valuable because they extended the known arc of Uranus's orbit back much further in time. Since Uranus takes approximately 84 years to complete one circuit around the Sun, the 40 years of observations since 1781 covered less than half of a single orbit, which made it difficult to determine the orbital parameters with great precision. The addition of Flamsteed's observation from 1690 and Lemonnier's observations from the mid-18th century meant that astronomers now had data spanning well over a century, more than enough to encompass a complete orbit and thereby pin down the shape and orientation of Uranus's elliptical path. And yet, when Alexis Bouvard sat down to calculate the orbit, he encountered a troubling difficulty. He could not find a single set of orbital elements that would fit both the old observations and the new ones. If he adjusted his calculations to match the pre-discovery sightings, the more recent observations would disagree by unacceptable amounts. If he fitted his orbit to the post-1781 data, then the positions recorded by Flamsteed and Lemonnier would be significantly in error. Something was not right, and Bouvard was forced to make a choice. He decided, in the end, to base his tables primarily on the newer observations, which he considered more reliable given the improvements in telescopes and techniques over the intervening years. The older observations, he suggested, might contain systematic errors that rendered them less trustworthy. This was a reasonable assumption, and his tables were published with the expectation that they would serve astronomers well for many years to come. For a time, Bouvard's tables did their job adequately, but as the 1820s gave way to the 1830s and the 1830s to the 1840s, the discrepancies between prediction and observation began to grow once more, and this time they could not be blamed on the old data. Astronomers using the best instruments available were finding that Uranus was simply not where Bouvard's tables said it should be. The errors were small in absolute terms, amounting by the early 1840s to roughly 2 arc-minutes, which is to say about 1/15 of the apparent diameter of the full moon. To the casual observer, this might seem an almost negligible amount, but to astronomers accustomed to measuring positions with a precision of a few arc-seconds, a discrepancy of 2 arc-minutes was enormous, representing an error perhaps 60 times larger than the accuracy of their instruments. Something was clearly wrong, either with the observations, with the calculations, or with the fundamental understanding of how gravity worked at such immense distances from the Sun. Several explanations were proposed to account for this troublesome wandering of Uranus from its predicted path. One possibility, though it was never taken very seriously by most astronomers, was that Newton's law of gravitation might not hold exactly true at the great distances involved. Perhaps, some suggested, the inverse square relationship that Newton had established, whereby the force of gravity decreases with the square of the distance between two objects, might require some small modification when applied to regions of space so far from the Sun. This idea had a certain appeal because it would explain why the discrepancy had not been noticed with the inner planets, which orbit much closer to the Sun, but most scientists were reluctant to abandon or modify such a well-tested and beautifully simple law without very compelling evidence. Another suggestion involved the hypothetical cosmic ether, that subtle medium which many physicists of the era believed permeated all of space and through which light waves were thought to propagate. Perhaps, it was proposed, this ether offered some slight resistance to the motion of bodies traveling through it, and perhaps this resistance was more noticeable for Uranus because of its greater distance and slower orbital velocity. But this explanation, too, failed to gain much traction, for it was unclear why such an effect would produce the particular pattern of deviations that were being observed, with Uranus sometimes running ahead of its predicted position and sometimes falling behind. A more dramatic possibility was that Uranus had at some point in the past suffered a collision with a comet, which had given it a sudden kick and altered its orbit in ways that the astronomers' calculations had not accounted for. Comets were known to occasionally pass through the inner solar system, their appearances recorded since ancient times, and it was not unreasonable to suppose that one might have struck a planet. But this explanation had its own difficulties, for a collision violent enough to produce the observed discrepancies would likely have left other traces, and besides, the deviations of Uranus had been growing steadily over time, which was not the pattern one would expect from a single impulsive event in the past. The explanation that gradually came to seem most promising to many astronomers was the possibility that Uranus was being pulled off course by the gravitational attraction of another planet, one that had not yet been discovered, orbiting somewhere beyond Uranus in the cold outer reaches of the solar system. This idea had a certain elegant simplicity to it, for it required no modification of the known laws of physics and proposed only the existence of an additional body of the sort that was already familiar. The gravitational influence of Jupiter and Saturn on Uranus had already been taken into account in Bouvard's calculations, and if there existed another large planet further out, its pull would introduce additional perturbations that could explain the observed deviations. Not everyone was convinced by this hypothesis, however, and among the skeptics was George Biddell Airy, who held the prestigious position of Astronomer Royal of England from 1835 onwards. Airy was a formidable figure in British astronomy, meticulous and hard-working, with strong opinions about how astronomical research should be conducted. He was initially doubtful that the irregularities in the motion of Uranus could be explained by an unknown planet, and he raised various objections to the hypothesis. Among other things, Airy pointed out that the problem of working backwards from observed perturbations to deduce the position of the perturbing body was extraordinarily difficult mathematically, and he was not certain that a reliable solution could be obtained. He was also, perhaps, somewhat territorial about matters relating to positional astronomy, and he may have been reluctant to see mathematical theorists from outside the observatory community claiming authority on such questions. Airy's skepticism was influential, given his position and reputation, and it may have contributed to a certain hesitation among British astronomers to pursue the transuranian planet hypothesis vigorously. But not everyone shared his doubts. On the continent, the great German astronomer and mathematician Friedrich Wilhelm Bessel had become interested in the problem and had recognized its potential significance. Bessel was one of the foremost astronomers of his generation, famous for his precise measurements of stellar positions and for being the first to measure the parallax of a star, thereby determining its distance from Earth. He understood the mathematical challenges involved in the inverse perturbation problem, but he believed it might be tractable, and he intended to investigate it seriously. Sadly, Bessel's health had been failing for some years, and before he could make substantial progress on the Uranus problem, he passed away in March of 1846, leaving the investigation to others. His interest, however, had signaled to the astronomical community that the question was a worthy one, and by the mid-1840s, several talented mathematicians had independently begun to tackle the challenge. The stage was set for one of the most dramatic episodes in the history of astronomy, though the participants themselves could not have known how events would unfold. For now, Uranus continued its slow journey around the Sun, deviating gently but persistently from its expected path, a quiet puzzle written in the language of arc minutes and orbital mechanics, waiting patiently for someone to read its meaning. And so we arrive at one of the quieter marvels in the history of astronomy, a story not of sudden revelation or fortunate accident, but of patient calculation, of long hours spent with quill and paper, working through equations that described the invisible pull of a world no human eye had ever knowingly seen. This is the story of two young men, working independently in different countries, who each set themselves the extraordinary task of finding a planet through mathematics alone, of reasoning backwards from the tiny wobbles in Uranus's path to deduce where an unknown body must be lurking in the darkness beyond. In the summer of 1841, a young Englishman named John Couch Adams was browsing through a bookshop in Cambridge when he came across a report by George Airy, the Astronomer Royal, which discussed the troubling irregularities in the motion of Uranus. Adams was 22 years old at the time, an undergraduate at St. John's College who had already distinguished himself as a mathematician of unusual ability, the sort of student who worked through problems with a steady, methodical determination that his tutors found most promising. Something about that report captured his imagination, and he made a note to himself, a memorandum that he kept for many years afterward, in which he recorded his intention to investigate the irregularities in Uranus's motion as soon as he had taken his degree, to see whether they might be explained by the gravitational influence of an undiscovered planet lying somewhere beyond. This was not a small ambition. The mathematics involved were formidable, requiring Adams to work backwards from observed effects to unknown causes, a process that astronomers call inverse perturbation theory. When you know where two planets are and wish to calculate how they will affect each other's motions, the problem is already demanding but at least straightforward in principle. You apply Newton's laws, you work through the geometry, you compute the gravitational attractions and their effects on each orbit. But Adams was attempting something far more difficult. He knew only the effects, the small deviations of Uranus from its predicted path, and from these subtle disturbances, he hoped to deduce the position and mass of a planet that might be causing them. It was rather like trying to determine the location and weight of an invisible person standing in a room by observing the slight trembling of the floorboards beneath your feet. Adams completed his undergraduate studies in 1843, earning the highest honors that Cambridge could bestow upon a mathematician, and almost immediately he began work on the problem that had been waiting patiently in his notebook. He spent the better part of 2 years on his calculations, refining his methods, checking and rechecking his arithmetic, gradually narrowing down the region of sky where the unknown planet should be found. By September of 1845, when Adams was still only 26 years old, he had completed his first solution. According to his calculations, a planet of substantial size should be located at a particular position in the constellation of Aquarius, and if astronomers would only point their telescopes at that region, they would find it there, a small disk of light distinguishable from the fixed stars by its slow motion against the background of more distant objects. Here is where the story takes a melancholy turn, not through any dramatic catastrophe, but through a series of small failures, missed connections, and unfortunate misunderstandings that would delay the recognition of Adams's achievement by more than a year. In the autumn of 1845, Adams attempted to share his results with two of the most important astronomers in England, James Challis, who directed the Cambridge Observatory, and George Airy, the Astronomer Royal at Greenwich. Neither man gave Adams the response he had hoped for, though their reasons were somewhat different. Challis was a competent astronomer who had known Adams for some time and thought well of his mathematical abilities, but he seems to have been rather overwhelmed by the demands of running the observatory and did not fully appreciate the significance of what Adams was offering him. When Adams showed him the predicted position for the new planet, Challis expressed polite interest but took no immediate action to search for it. The Cambridge telescope was certainly capable of revealing Neptune if only someone had thought to look carefully enough, but the search was never conducted with the systematic thoroughness that the situation required. Adams's attempt to communicate with Airy was even less successful. In October of 1845, Adams travelled to Greenwich twice in hopes of meeting with the Astronomer Royal, but Airy was not at home on either occasion, and Adams, being a shy and rather diffident young man, felt uncomfortable leaving his carefully prepared results with a servant. He did eventually send Airy a summary of his calculations, and Airy responded with a letter asking for clarification on a technical point, specifically whether Adams's solution could explain certain irregularities in the radius vector of Uranus, the planet's distance from the Sun at various points in its orbit. For reasons that have never been entirely clear, Adams did not reply to this query, perhaps because he felt the question missed the point, or perhaps because his natural reticence made correspondence with the formidable Astronomer Royal something of an ordeal. Whatever the reason, the exchange simply stopped, and Airy concluded that Adams's work was perhaps not as complete or reliable as it might have been. And so the months passed, with Adams's prediction sitting quietly in his notebooks and in the files of two English astronomers who had not quite grasped what they had been given. Meanwhile, in Paris, another young mathematician had begun work on the very same problem, entirely unaware that anyone else was pursuing it. His name was Urbain Jean-Joseph Le Verrier, and he would prove to be both Adams's greatest rival and, in a certain sense, his closest intellectual companion, for the two men were engaged in an identical quest, separated by the English Channel but united by their faith in the power of Newtonian mathematics to reveal the hidden architecture of the solar system. Le Verrier was 34 years old when he turned his attention to Uranus, somewhat older than Adams but still young for such an ambitious undertaking. He had trained as a chemist before discovering his true vocation in celestial mechanics, and he brought to astronomy a fierce intensity and an uncompromising rigor that could be both admirable and rather difficult for his colleagues to endure. Le Verrier was not, by most accounts, an easy man to work with. He had a sharp tongue and a certain impatience with those he considered less capable than himself, which unfortunately included most of the people he encountered. His manner could be brusque, his criticism stinging, and over the course of his career he would alienate so many of his fellow astronomers that he would eventually be forced to resign from the directorship of the Paris Observatory, only to be reinstated years later when his successor proved even more unpopular. But whatever his personal difficulties, Le Verrier was a mathematician of formidable skill, and when he set his mind to the problem of Uranus, he attacked it with a systematic thoroughness that would ultimately prove decisive. In November of 1845, just a few weeks after Adams had failed to connect with Airy at Greenwich, Le Verrier presented the first of 3 memoirs to the French Academy of Sciences, laying out his preliminary analysis of the Uranus problem and his plan for solving it. A second memoir followed in June of 1846, in which Le Verrier refined his calculations and narrowed the predicted position of the unknown planet. And on the last day of August in that same year, he presented his third and final memoir, which gave a precise location for the planet along with an estimate of its mass and the characteristics of its orbit. Both Adams and Le Verrier, working independently and using similar mathematical techniques, had arrived at predictions that placed the unknown planet in roughly the same region of the sky. Adams's calculated position was within about 2 degrees of Neptune's actual location, a remarkable achievement given the complexity of the problem and the uncertainties in the data. Leverrier's prediction was even more precise, placing the planet within about 1 degree of where Johann Galle would eventually find it. These were extraordinary results, and they demonstrated beyond any reasonable doubt that the disturbances in Uranus's motion could be explained by the gravitational influence of a single massive body orbiting at a distance well beyond Uranus itself. It is worth pausing for a moment to appreciate the mathematical technique that made these predictions possible, even though the details are rather too involved for a complete explanation here. The basic approach was to assume that the unseen planet followed a roughly circular orbit at a distance from the Sun that could be estimated using Bode's law, the empirical rule that had correctly predicted the approximate distances of several planets, including Uranus. Both Adams and Leverrier made this assumption, choosing distances of about 36 to 38 astronomical units, which is to say 36 to 38 times the average distance from Earth to the Sun. This assumption, as it turned out, was actually rather far from the truth, since Neptune orbits at a distance of only about 30 astronomical units, considerably closer than either mathematician had supposed. The fact that both predictions placed Neptune in approximately the correct position despite this error in distance is one of the more curious aspects of the story, and it has been the subject of considerable discussion among historians of astronomy. The explanation appears to be that the errors in the assumed distance happen to be compensated, at least temporarily, by other aspects of the orbital calculations, so that the predicted position remained reasonably accurate even though the predicted orbit was substantially wrong. This was something of a fortunate coincidence, a case where 2 wrongs happened to make something close to a right, at least for the purposes of locating the planet in the autumn of 1846. With his final memoir presented to the Academy, Leverrier now faced the problem of convincing someone to actually search for his predicted planet. One might suppose that the astronomers of Paris would have been eager to claim such a discovery for France, but the reality was rather different. Leverrier's difficult personality had made him few friends among his colleagues, and the French observatories showed little enthusiasm for undertaking a systematic search on his behalf. The Paris Observatory possessed an excellent map of the region of sky where Leverrier believed the planet should be found, but no one there seemed willing to devote the necessary time and effort to looking for it. Days passed, and then weeks, with the planet hanging there in the darkness, waiting to be discovered, while Leverrier grew increasingly frustrated at the lack of action. It was this frustration that led Leverrier to write to Johann Galle at the Berlin Observatory, setting in motion the events that would culminate in the actual discovery of Neptune. But that is a matter for the next part of our story, and for now it is enough to rest with the remarkable fact that 2 young mathematicians, working on opposite sides of a narrow sea, had each calculated the position of a world that neither had ever seen, reasoning from the subtle perturbations in the motion of Uranus to the existence and location of something that had been entirely unknown. They had proved that Newton's laws could reach beyond the visible planets, that the mathematics of gravitation could extend into the darkness and bring back knowledge of what lay hidden there. It was a triumph of patient calculation, of long hours spent with equations and logarithm tables, and it remains one of the most beautiful examples of the power of mathematical reasoning to reveal truths about the physical world that would otherwise remain forever beyond our grasp. On the morning of September 23, 1846, a letter arrived at the Berlin Observatory, having made its way from Paris through the ordinary postal routes that connected the astronomical institutions of Europe. The letter bore the name of Urbain Le Verrier, and it was addressed to Johann Gottfried Gall, a young astronomer who had previously sent Le Verrier a copy of his doctoral dissertation as a gesture of professional courtesy. Le Verrier was now returning that courtesy in a most extraordinary fashion, for his letter contained not merely pleasantries or theoretical discussions, but rather a set of precise coordinates where he believed an unknown planet might be found. The predicted position placed this hypothetical world in the constellation Aquarius, and Le Verrier expressed his hope that Gall might be willing to direct a telescope toward this region of the sky and search for the object that his calculations insisted must exist there. Gall read the letter with considerable interest, for he was well aware of the work that Le Verrier had been conducting on the irregularities in the orbit of Uranus. The mathematics involved were formidable, requiring months of painstaking calculation, and the conclusion that Le Verrier had reached was nothing short of remarkable. He was claiming that the gravitational influence of an unseen planet was responsible for the observed perturbations, and he was now confident enough in his work to provide a specific location where astronomers might look. The coordinates suggested right ascension of 22 hours and 46 minutes, with a geocentric longitude of approximately 326 degrees, and Le Verrier estimated that the planet would present itself as an object of perhaps the 8th or 9th magnitude, which would place it just beyond the reach of naked eye visibility but well within the capability of a modest telescope. The Berlin Observatory possessed an excellent refracting telescope with an aperture of 9 inches, which had been constructed by the renowned optician Joseph von Fraunhofer and represented one of the finest instruments available to European astronomers at that time. However, Gall was not the director of the observatory, and he could not simply commandeer the telescope for his own purposes without first obtaining permission. The director was Johann Franz Encke, a distinguished astronomer who had made significant contributions to the study of comets and who maintained careful oversight of how the observatory's resources were allocated. Gall approached Encke on that same day, September 23, and explained the contents of Le Verrier's letter, requesting permission to use the Fraunhofer refractor that evening to search for the predicted planet. Encke was initially somewhat hesitant, for the observatory had its regular program of observations to conduct, and the search for a hypothetical planet based on theoretical predictions alone might have seemed to some a speculative venture. Yet the confidence with which Le Verrier had stated his case, combined with the precision of his coordinates, apparently persuaded Encke that the attempt was worthwhile. It happened also to be Encke's birthday on that particular evening, and whether this circumstance contributed to a mood of generosity or whether he was simply convinced by the scientific merit of the proposal, Encke granted Gall permission to conduct the search. The telescope would be available after the completion of the night's scheduled observations, and Gall could direct it toward the region of Aquarius that Le Verrier had specified. As Gall prepared for the evening's work, he was joined by a young student named Heinrich Louis d'Arrest, who had been assisting with various projects at the observatory and who expressed a keen desire to participate in the search. D'Arrest was 24 years old at the time, having been born in Berlin in 1822, and he would go on to have a distinguished career in astronomy. But on that September evening he was simply an eager assistant hoping to be present for what might prove to be a significant discovery. His involvement would prove to be rather more consequential than mere presence, however, for it was d'Arrest who made a suggestion that would dramatically improve the efficiency of their search. The fundamental challenge in searching for an unknown planet among the stars is that a distant planet, when viewed through a telescope, appears as nothing more than a point of light, superficially indistinguishable from the thousands of stars that populate any given region of the sky. To identify a planet, one must either detect its motion relative to the background stars, which requires observations on multiple nights, or one must notice that it does not appear on existing star charts, which requires having access to sufficiently detailed and accurate charts of the region in question. d'Arrest suggested that they make use of a recently published star chart prepared by Carl Bremiker, which covered the very region of Aquarius where Verrier had predicted the planet would be found. This chart, designated Hora 21 in the series being produced by the Berlin Academy, had only recently been printed and distributed, and it represented one of the most accurate and complete surveys of that portion of the sky then available. The existence of this particular chart at the Berlin Observatory on that particular night was a fortunate circumstance, for the chart had been completed only recently and copies had not yet reached many other observatories. Chalice in Cambridge, for instance, did not have access to this updated chart, and this absence would prove to be significant in understanding why the Cambridge search had thus far failed to identify the planet despite having observed it. But at Berlin, the chart was available, and d'Arrest's suggestion to employ it would transform what might have been a lengthy and uncertain search into an efficient and systematic comparison of the telescopic field with the charted positions of known stars. The observation session began in the early evening hours, once the sky had darkened sufficiently for the fainter stars to become visible. Gall positioned the telescope according to Verrier's coordinates and began calling out the positions and approximate magnitudes of the stars he observed in the field of view. d'Arrest sat nearby with the Bremiker chart spread before him, checking each star that Gall reported against the positions marked on the chart. Star after star was identified and confirmed, each one matching a corresponding entry in the catalogue, and for some time the search proceeded without incident. The process required patience and careful attention, for the field was populated with numerous faint stars, and each one needed to be verified before moving on to the next. Then, approximately 30 minutes after they had begun their systematic search, Gall reported observing a star of the 8th magnitude at a position that did not correspond to any star marked on the chart. d'Arrest checked the position again, running his finger across the chart to be certain he had not overlooked an entry, but there was no star recorded at that location. The object that Gall was observing through the telescope appeared to be of the 8th magnitude, which matched Verrier's prediction quite closely, and its position was less than 1 degree away from the coordinates that Verrier had specified. The agreement was remarkable, and both Gall and d'Arrest recognized immediately that they might well be looking at the planet whose existence Verrier had deduced from mathematics alone. To confirm that the object was indeed a planet rather than a previously uncatalogued star, they needed to establish either that it showed perceptible motion or that it displayed a visible disk rather than the point-like appearance of a star. Gall examined the object carefully through the telescope, increasing the magnification to observe it more closely, and he noted that it did indeed present a small but discernible disk, which he estimated to be approximately 3 arcseconds in diameter. This was precisely the appearance one would expect from a distant planet, whose angular size would be small but nonetheless measurable, in contrast to the infinitesimal points of light presented by even the nearest stars. The presence of this disk provided strong evidence that the object was not a star but rather a body of significant physical extent seen at great distance. Further confirmation came on subsequent nights, when the object was observed to have shifted its position relative to the background stars, demonstrating the proper motion of a body in orbit around the Sun. But even on that first night, Gall and D'Arrest were sufficiently confident in their observation to recognize that they had likely found the planet that Verrier had predicted. Encke himself came to the telescope to view the object, and he too observed the small disk that distinguished it from the surrounding stars. The discovery had been accomplished within half an hour of beginning the systematic search, a testament both to the accuracy of Verrier's calculations and to the efficiency of the method that D'Arrest had proposed. Gall composed a letter to Verrier that same night or very shortly thereafter, informing him that the planet had been found. The letter conveyed the position of the observed object and noted its close agreement with the predicted coordinates, differing by less than 1 degree from where Verrier had said it would be. This letter would reach Verrier in Paris and provide him with the confirmation he had been awaiting, the empirical verification that his months of calculation had correctly identified the location of a previously unknown world. The discovery represented a triumph of theoretical astronomy, demonstrating that the methods of celestial mechanics could be used not merely to explain observed phenomena but to predict the existence of bodies that had never been seen. Meanwhile, in Cambridge, James Challis had actually observed the planet on at least 2 occasions during the preceding month of August, yet he had failed to recognize it as anything other than an ordinary star. Challis had been conducting his search in a methodical but laborious fashion, recording the positions of stars in the predicted region with the intention of comparing his observations over time to detect any object that had moved. However, he had not performed this comparison in a timely manner, and he lacked access to the updated star charts that might have allowed him to identify the planet immediately. The Bremiker chart that proved so valuable at Berlin was not available to Challis, and his own observations were too numerous and too poorly organized for him to notice that one particular point of light appeared in a position where no star should be. The irony of the situation was considerable, for Challis had possessed the advantage of receiving Adams's predictions well before Verrier's work was published, yet he had squandered this advantage through a combination of inadequate resources and insufficient urgency. When news of the Berlin discovery reached Cambridge, Challis reviewed his records and discovered to his chagrin that he had observed the planet on August 4 and August 12, recording its position both times without recognizing its significance. Had he compared these observations to one another, he would have noticed that the object had moved, and the discovery would have been credited to British rather than German astronomers. As it was, the honor belonged to Gall and D'Arrest, working on behalf of Verrier's prediction. The question of what to name the newly discovered planet occasioned some disagreement among astronomers. Verrier initially proposed that the planet be named after himself, which would have been a significant departure from the tradition of naming planets after figures from classical mythology. He later suggested the name Neptune, but also continued to advocate for his own name, and for a time he even began referring to Uranus as Herschel, after its discoverer, apparently in an attempt to establish a precedent for naming planets after astronomers. British astronomers, perhaps influenced by their disappointment at having missed the discovery, proposed the name Oceanus, which would have maintained the mythological tradition while providing a distinctively British contribution to the nomenclature. The German astronomers at Berlin were content to use whatever name gained general acceptance. In the end, the name Neptune prevailed, being proposed by various parties and gradually adopted by the astronomical community over the following months. Neptune was the Roman god of the sea, brother to Jupiter and Pluto in the classical mythology, and the name seemed appropriate for a planet that occupied the distant reaches of the solar system, far beyond the warmth of the sun in the cold outer regions where the ancient astronomers had never thought to look. The controversy over naming eventually subsided, and Neptune took its place in the catalogue of known planets, the first to have been discovered through the power of mathematical prediction rather than the patient scanning of the heavens. The night of September 23, 1846, thus marked a turning point in the history of astronomy, demonstrating that the universe could be comprehended through reason and calculation, that the motions of distant worlds could be deduced from the subtle influences they exerted on their neighbors, and that the human mind could reach out across the vastness of space to find what the eye alone could never see. And so, as the news of Neptune's sighting at Berlin spread across the learned circles of Europe in those final days of September 1846, what might have been a moment of pure scientific celebration became instead entangled in questions of priority and national honor, in wounded feelings and defensive explanations, in the sort of human complications that so often accompany great discoveries, reminding us that even the most abstract and mathematical of achievements are made by people with reputations to protect and colleagues to answer to and countries whose scientific standing they feel obliged to uphold. The trouble began, as such troubles often do, with a letter. On the 3rd of October, 1846, just 10 days after Gall had found Neptune in his telescope, Sir John Herschel, the son of William Herschel who had discovered Uranus all those decades before, wrote to a publication called the Athenaeum, a weekly journal of literature and the arts that also covered matters of science and learning, and in this letter Herschel revealed something that many in Britain had known for some months but that the wider world, and particularly the French, had not been told, namely that a young mathematician at Cambridge named John Couch Adams had performed calculations very similar to those of Verrier, and had done so earlier, and had communicated his results to the Astronomer Royal and to the director of the Cambridge Observatory well before Verrier's final paper had appeared. Herschel's letter was well-intentioned, one might suppose, a simple desire to ensure that a deserving young Englishman received his share of credit for what was clearly a remarkable intellectual achievement, but the effect of this revelation was rather like dropping a stone into still water and watching the ripples spread outward in ever-widening circles of consternation and accusation. The French were, to put it gently, displeased. From their perspective, Verrier had published his work openly, had specified the location where the new planet should be found, had written to the Berlin Observatory with his prediction, and had been vindicated when Gall pointed his telescope at precisely that spot and found Neptune waiting there, just where Verrier had said it would be. And now, only after this triumph, the British were coming forward to claim that one of their own had actually done it first, though he had published nothing, though no telescope had been directed to any position he had specified, though the discovery had been made entirely on the basis of Verrier's calculations and nobody else's. François Arago, the director of the Paris Observatory and a figure of considerable influence in French scientific circles, responded with particular vigor, defending Verrier's claim to sole credit with a passion that reflected not only his personal loyalty to his younger colleague but also a certain patriotic feeling that French science was being robbed of its rightful glory by perfidious English maneuvering. Arago declared that Verrier was the true and only discoverer of the new planet, that the belated British claims were an attempt to diminish French achievement through what he considered bad faith, and that Adams, whatever calculations he might or might not have made in the privacy of his rooms at Cambridge, could not be considered a discoverer of something he had never actually enabled anyone to discover. The French press took up this theme with enthusiasm, and for a time the scientific correspondence between the two countries took on a distinctly frosty tone, with accusations of concealment on one side and of jealousy on the other, all of which must have been rather uncomfortable for the two young mathematicians at the center of the dispute, neither of whom had sought controversy and both of whom were, by temperament, more interested in the elegant certainties of celestial mechanics than in the messy business of priority claims. Adams, for his part, maintained throughout this unpleasant episode a dignified silence that speaks well of his character, declining to enter into public disputes about who had done what first and when, declining to make accusations against those who had failed to act on his predictions, declining to blame either Airy for his delay or Challis for his incomplete searching, though he might reasonably have felt aggrieved at both, and simply continuing with his mathematical work as though the controversy were happening to someone else entirely. This restraint, this refusal to engage in recrimination, gradually earned Adams considerable respect even among those who had initially dismissed his claims, and as the months passed and tempers cooled, a more measured assessment of the situation began to emerge among fair-minded observers in both countries. The following year, in 1847, Adams and Verrier met for the first time, and this meeting, which might have been awkward or hostile given all that had been said and written, proved instead to be the beginning of a genuine friendship between two men who recognized in each other a kindred spirit, a fellow traveler in the rarefied world of mathematical astronomy, someone who could truly appreciate the intellectual challenges they had each confronted and overcome. Verrier, whatever his initial feelings about the British claims, was too good a mathematician not to recognize that Adams had indeed solved the same problem by similar methods, and Adams, for his part, freely acknowledged the superiority of Verrier's position in terms of publication and practical impact, and the two of them seemed to have reached an understanding that transcended the nationalistic squabbling of their respective champions, an understanding based on mutual respect for each other's abilities and a shared recognition that the universe was large enough to accommodate more than one discoverer. But if Adams emerged from the controversy with his reputation enhanced by his gracious conduct, the same could not be said for George Biddell Airy, the Astronomer Royal, whose role in the affair came under increasingly critical scrutiny as the details of what had happened became more widely known. Airy found himself in the uncomfortable position of having to explain why he had not acted more promptly on Adams's predictions, why he had not directed the resources of Greenwich Observatory toward searching for the predicted planet, why he had instead posed a somewhat pedantic question about the radius vector and then apparently lost interest when Adams failed to respond immediately, and why, even after Challis had begun searching at Cambridge, Airy had not coordinated more effectively with him or impressed upon him the urgency of checking his observations against star catalogues. In October and November of 1846, Airy prepared and circulated a detailed account of his involvement in the affair, a document that sought to justify his actions and to explain the reasoning behind his decisions, but this defensive explanation satisfied few of his critics and left many with the impression that the Astronomer Royal, through excessive caution or bureaucratic rigidity or perhaps simple failure of imagination, had allowed a great discovery to slip through British fingers. Airy's reputation, which had been high before the Neptune affair, suffered lasting damage from this episode, and for the rest of his long career he would be associated in the public mind with a missed opportunity, with a failure to recognize the significance of what had been placed before him, though it should be said in fairness that Airy was far from the only person who might have acted differently, and that the full story of what happened in those crucial months is rather more complicated than the simple narrative of negligence might suggest. And here we come to a curious chapter in the history of this history, a development that occurred more than a century and a half after the events themselves, when documents that had long been missing from the archives at Greenwich were unexpectedly discovered in Chile, of all places, among the papers of a later astronomer who had apparently taken them from the observatory's files without authorization. These documents, which came to be known as the Neptune Papers, were found in 1998 and returned to their proper home at Cambridge, and when historians examined them carefully they found that they shed new light on several aspects of the affair, particularly on the actions of both Challis and Airy during the critical period when Adams's predictions might have led to a British discovery of Neptune. The papers revealed, among other things, just how close Challis had come to recognizing Neptune among his observations, and how administrative confusion and inadequate record-keeping had contributed to the failure to identify it sooner, and they provided additional context for Airy's decisions that made his conduct appear perhaps somewhat more understandable, if no less unfortunate in its consequences. The discovery of these long-lost documents served as a reminder that historical understanding is always provisional, always subject to revision as new evidence comes to light, and that even the most thoroughly studied episodes may contain surprises waiting in forgotten files and mislabeled boxes and the papers of people who have carried away pieces of the story without anyone realizing they were gone. In the years since the Neptune papers came to light, historians of science have continued to refine their understanding of the priority dispute and its significance, and a modern consensus has emerged that attempts to do justice to both Adams and Verrier while acknowledging the important differences in their situations. That consensus holds that both mathematicians deserve credit for independently solving the same extraordinarily difficult problem, for demonstrating that the perturbations of Uranus could be explained by the gravitational influence of an unseen outer planet, and for calculating with remarkable accuracy where that planet should be found in the sky, and in this sense the intellectual achievement is shared between them, a tribute to the power of Newtonian mechanics and to the mathematical skill of two young men working in ignorance of each other's efforts. But the consensus also recognizes that there is a meaningful difference between work that is published and work that remains private, between predictions that lead directly to discovery and predictions that remain untested in observatory records, between science that is communicated to the world and science that circulates only among a small circle of acquaintances. And in this sense Leverrier's claim has a priority that Adams's does not, for it was Leverrier's published coordinates that enabled Gall to find Neptune, and it was Leverrier's papers that established the methodology for all to examine and verify. This distinction matters not because Adams was any less talented or his calculations any less correct, but because science, in the end, is a communal enterprise, a shared endeavor that depends on open communication and public scrutiny and the ability of others to build upon what has been established, and work that is not published, however brilliant, cannot contribute to this communal enterprise in the same way that work which is published can. The controversy over Neptune's discovery had, in the end, a salutary effect on scientific communication practices, serving as a cautionary tale about the importance of timely publication, about the need to make predictions public before discoveries are made rather than after, about the risks of allowing institutional caution or personal modesty to delay the dissemination of significant results. In the decades that followed, scientists became increasingly conscious of the need to establish priority through publication, to document their work in ways that could be dated and verified, to avoid the sort of ambiguity that had allowed the Neptune dispute to become so bitter and prolonged. The modern system of scientific journals with their submission dates and peer review and careful attribution owes something to this episode, as do the practices of preprint servers and conference presentations and all the other mechanisms by which scientists today announce their findings to the world and establish their claims to have been first. And so, as you settle deeper into your pillow and feel the gentle weight of drowsiness beginning to press upon your eyelids, you might reflect for a moment on this very human story that played out against the backdrop of celestial mechanics and orbital perturbations, on the wounded pride and national feeling and personal rivalries that accompanied one of the great triumphs of mathematical astronomy, and on how, in the end, the two principal figures found their way to mutual respect and friendship, recognizing that they had more in common with each other than with the partisans who fought on their behalf. The stars continued in their courses, Neptune continued in its slow orbit around the distant Sun, and the controversy that had seemed so important in the autumn of 1846 gradually faded into the footnotes of history, leaving behind only the achievement itself, the demonstration that mathematics and observation together could reveal the existence of worlds that no eye had ever seen, that the universe could be known not only through watching but through calculating, through the patient application of reason to the evidence of the senses, through the willingness to believe that nature follows laws that the human mind can discover and articulate and use to predict what lies beyond the range of present vision. In the weeks that followed the confirmation of Neptune's existence, the astronomical world turned its attention toward understanding this newly revealed giant, this distant sphere of pale light that had waited so patiently at the edge of the known solar system. The initial excitement of discovery gave way to something quieter and perhaps more meaningful, the slow, careful work of observation and measurement that would gradually reveal what sort of world Neptune truly was. And it was here, in these early studies, that astronomers began to uncover details both expected and surprising, details that would shape our understanding of the outer solar system for generations to come. Among the first to turn a powerful telescope toward the new planet was William Lassell, a brewer by trade who had accumulated sufficient wealth to pursue his true passion, the construction and operation of large reflecting telescopes. Lassell had built his observatory in Liverpool, a city not particularly known for its clear skies or steady air, and yet through determination and considerable skill, he had equipped it with a 24-inch reflector of his own design and manufacture. This was a substantial instrument for its time, with a mirror ground and polished by Lassell himself using techniques he had developed through years of patient experimentation. The telescope gathered enough light to reveal details invisible to smaller instruments, and Lassell was eager to examine the eighth planet before it drifted too far from opposition and became more difficult to observe. Just 17 days after Johann Galle and Heinrich d'Arrest had first identified Neptune in Berlin, on the 10th of October in 1846, Lassell detected a faint point of light near the planet's disk. He suspected immediately that this might be a satellite, a moon circling Neptune just as our own moon circles Earth, just as the four great moons circle Jupiter and the known satellites accompany Saturn. Over the following nights, Lassell observed carefully, watching the tiny point shift its position relative to Neptune in a manner consistent with orbital motion rather than the steady drift of a background star. By early November, he was confident enough in his observations to report the discovery, and other astronomers with sufficiently powerful instruments were able to confirm what he had seen. This moon would eventually receive the name Triton, drawn from Greek mythology as befitting a satellite of the sea god Neptune. Triton was not a small moon but rather a substantial world, larger as it would turn out than the planet Pluto that would be discovered many decades later. From the very beginning, there was something unusual about Triton's orbit, something that set it apart from nearly every other large satellite in the solar system. As astronomers accumulated observations and calculated the moon's path around Neptune, they found that Triton orbited in the retrograde direction, moving clockwise when viewed from above Neptune's north pole rather than counterclockwise as nearly all other major moons do around their parent planets. This retrograde motion was puzzling and would remain so for many years. In the orderly universe of Newtonian mechanics, moons were expected to orbit in the same direction that their planet rotated, having formed from the same swirling disk of material that coalesced into the planet itself. A retrograde orbit suggested a different origin entirely, perhaps that Triton had not formed alongside Neptune but had instead been captured, drawn in from an independent orbit around the Sun and trapped by Neptune's gravity through some complex gravitational interaction. This capture hypothesis would gain support over time as astronomers came to understand more about the outer solar system and the populations of icy bodies that inhabit it. Triton's retrograde path through space, so different from the prograde motion of other large moons, hinted at a violent and dynamic history quite different from the gentle accretion imagined for most planetary satellites. Lassell continued his observations of Neptune through the following months, his dedication to the work unwavering despite the challenging conditions of English weather. In 1846 and again in 1847, he reported seeing what he believed to be a second satellite, a fainter companion to Triton moving in a different orbit around the planet. This second moon was announced with appropriate caution, as Lassell was a careful observer who understood the difficulties of detecting faint objects near a brighter source, and yet he felt confident enough in his repeated observations to bring them before the astronomical community. However, despite numerous attempts by Lowell himself and by other observers with comparable instruments, this second satellite could never be reliably confirmed. Over time, the astronomical consensus settled on the conclusion that Lowell had been mistaken, that what he had seen was perhaps a background star briefly aligned with Neptune, or an artifact of atmospheric distortion, or some subtle flaw in his optical system that created a phantom companion. The spurious second moon passed into history as a cautionary tale about the difficulties of observation at the very limits of instrumental capability, a reminder that even skilled and honest observers could be deceived by the subtle interplay of light and glass and expectation. Meanwhile, other astronomers were studying Neptune's disk itself, trying to discern whatever features might be visible on that tiny blue-green circle of light. The color of Neptune was apparent from the earliest observations, a distinct blue-green tint quite different from the pale yellow of Jupiter and Saturn or the reddish hue of Mars. This coloration suggested something about the composition of Neptune's atmosphere, hinting at the presence of compounds that absorbed red light while reflecting blue, though the specific chemistry would not be understood for many decades. The disk itself showed no obvious features in most observations, no bands or spots or storms visible through the shimmering of Earth's atmosphere, and this featurelessness made it difficult to determine how quickly Neptune rotated on its axis. Astronomers attempted various methods to estimate Neptune's rotation period, looking for any slight changes in brightness or any temporary markings that might serve as reference points. Some observers reported seeing darker regions or lighter patches that appeared to shift position from night to night, and from these reports various rotation periods were proposed, typically ranging from about 14 to 19 hours. These early estimates were remarkably close to the true value as we know it today, though the uncertainty at the time was considerable. Without clear persistent features to track across the disk, any measurement of rotation period remained somewhat speculative, dependent on observations that pushed the limits of what 19th-century telescopes could reveal. As the months and years passed and astronomers accumulated more observations of Neptune's position against the background stars, they were able to refine their understanding of the planet's actual orbit. And here a curious situation emerged, one that would generate considerable discussion among celestial mechanicians. The predictions made by Adams and Verrier, which had successfully guided observers to Neptune's position in the sky, had been based on certain assumptions about the planet's orbit. Both mathematicians had assumed, reasonably enough given the limited information available to them, that Neptune's distance from the Sun would follow the pattern suggested by the Titius-Bode law, that curious numerical relationship which seemed to predict the orbital distances of the known planets with surprising accuracy. The Titius-Bode law, named for the German astronomers who had popularized it, was not truly a physical law at all but rather an empirical formula, a mathematical curiosity that happened to produce numbers close to the actual distances of Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, and Uranus. According to this formula, the next planet beyond Uranus should orbit at a distance of approximately 39 astronomical units from the Sun. Both Adams and Verrier had incorporated something close to this distance into their calculations, and their predictions had placed Neptune at roughly the right location in the sky for observers to find it. Yet as Neptune's actual orbit became clear through careful observation, it turned out that the planet was considerably closer to the Sun than the Titiusbode prediction suggested. Neptune's true orbital distance was approximately 30 astronomical units, significantly less than the 39 units that the mathematical formula would have indicated. This discrepancy raised an interesting question. If the assumed distance was wrong, how had the predictions succeeded in pointing observers to the correct patch of sky? The answer, as analysts came to understand, lay in a fortuitous coincidence of timing. In 1846, Neptune happened to be located in that portion of its orbit where the errors in the predicted orbital elements partially compensated for one another. The planet was closer than predicted but also moving faster, and during the particular years leading up to the discovery these factors combined in such a way that the predicted position and the actual position remained reasonably close together. Had the search been conducted a few decades earlier or later, the predictions might have been considerably less accurate, and the discovery correspondingly more difficult. This realization carried important implications for the philosophy of scientific prediction. The successful detection of Neptune had demonstrated the power of gravitational theory to predict the existence and location of unseen bodies, but the incorrect distance assumption showed that success in prediction did not necessarily mean that all underlying assumptions were correct. The Titiusbode law, which had seemed to receive such striking confirmation with the discovery of Uranus and the asteroid belt, was revealed to be something less than a fundamental principle of planetary arrangement. Neptune's orbit simply did not fit the pattern, and later discoveries would confirm that whatever regularity existed in the inner solar system did not extend reliably to the outer reaches. Yet even as Neptune's orbit became better understood, another problem began to emerge from the careful analysis of observational data. The whole purpose of predicting Neptune's existence had been to explain the irregularities in Uranus's motion, those persistent deviations from the calculated orbit that could not be attributed to the known planets. Neptune, massive and distant, had seemed the perfect explanation for these perturbations, and indeed the discovery of the eighth planet did account for much of the discrepancy. But not all of it. When astronomers incorporated Neptune's gravitational influence into their calculations of Uranus's orbit, small residual deviations remained. The fit was much better than before, but it was not perfect. These residual perturbations were subtle, near the limits of observational precision, and their interpretation was uncertain. Perhaps they represented nothing more than accumulated errors in the historical observations of Uranus, inaccuracies in the recorded positions that introduced apparent irregularities into the calculated orbit. Perhaps there were small systematic effects in the observational techniques that had not been fully accounted for. Or perhaps, and this was the intriguing possibility, there existed yet another planet beyond Neptune, even more distant and even more difficult to detect, whose gravitational pull was responsible for the unexplained residuals. The idea of a trans-Neptunian planet took root in the minds of several astronomers, though the practical difficulties of such a search were immense. If Neptune was barely visible as a faint point of light in the largest telescopes, any planet beyond it would be fainter still, perhaps indistinguishable from the millions of faint stars that crowded the photographic plates. The mathematical approach that had succeeded so brilliantly for Neptune would be far more challenging for a ninth planet, because the perturbations to be explained were smaller, the orbital period of the hypothetical perturber longer, and the range of possible solutions correspondingly greater. Nevertheless, several astronomers took up the challenge of predicting where such a planet might be found. William Henry Pickering, an American astronomer working at Harvard and later in Jamaica, developed a series of predictions for a trans-Neptunian planet beginning in the early 20th century. Pickering approached the problem systematically, analyzing the residuals in Uranus's motion and proposing various possible orbital solutions for a perturbing body. He published multiple predictions over the years, refining and sometimes contradicting his earlier work as new observational data became available. Other mathematicians and astronomers offered their own predictions, each based on slightly different assumptions and methods, creating a collection of possible locations for the hypothetical ninth planet. The search for this distant world would continue for decades, conducted by a handful of dedicated observers who photographed the sky night after night, comparing plates to look for the subtle motion that would betray a planet among the fixed stars. It was painstaking work, unglamorous and often unrewarding, yet those who pursued it understood that they were continuing a tradition begun by Adams and Verrier, seeking a world that mathematics suggested should exist even if no telescope had yet revealed it. And in the fullness of time, as we shall see, this patient search would bear fruit, though the nature of what was found would prove rather more complicated than anyone had anticipated. And so we come now to the story of Percival Lowell, a man of considerable wealth and even more considerable determination, who would spend the final decade of his life searching for a world he was certain must exist, somewhere out there in the darkness beyond Neptune, a world he called Planet X, and whose search would eventually lead, though not in his lifetime, to the discovery of Pluto, that small and distant body that would captivate the public imagination for generations to come. Percival Lowell was born in the year 1855 into one of the most distinguished families of Boston, Massachusetts, a family whose name was synonymous with the intellectual and social elite of New England, the sort of family that produced poets and scholars and captains of industry with equal regularity, and young Percival grew up in an atmosphere of privilege and expectation, surrounded by books and learning and the quiet assumption that he would make something significant of himself, as Lowell's always did. He attended Harvard University, as was expected, and there he studied mathematics, showing a particular aptitude for the precise and methodical work that mathematical inquiry demands, and this early training in careful calculation would prove essential in his later astronomical pursuits, though at the time he had no particular thought of spending his nights gazing at the stars. After completing his education, Lowell did not immediately turn to astronomy, but instead embarked upon a quite different sort of adventure, traveling to the Far East, where he spent nearly a decade immersed in the cultures of Japan and Korea, learning the languages, studying the customs, serving as a diplomat and counselor during a period of great change in that part of the world, and writing several well-regarded books about his experiences and observations. He was a keen observer of human societies, it seems, before he became a keen observer of celestial ones, and perhaps there was something in that early work, in the patient cataloguing of unfamiliar customs and the careful interpretation of subtle cultural signs, that prepared him for the equally patient work of scanning photographic plates for tiny points of light that might, just might, prove to be something more than ordinary stars. It was not until Lowell had reached his late 30s that astronomy captured his imagination entirely, and the catalyst for this transformation was the planet Mars, that rust-colored world that had fascinated observers since the time of the ancients. Lowell became convinced, after reading the work of the Italian astronomer Giovanni Schiaparelli, that the surface of Mars was crisscrossed with artificial channels, the work of an intelligent civilization struggling to survive on a dying world, and this romantic notion took hold of him with such force that he resolved to dedicate his fortune and his energies to proving it true. And so, in the year 1894, he established the Lowell Observatory in Flagstaff, Arizona, choosing that location for its high altitude and clear, dry air conditions that would allow him to observe the Martian surface with exceptional clarity during the planet's close approach to Earth. The observatory that Lowell built was a serious scientific institution, equipped with fine telescopes and staffed by capable astronomers, and Lowell himself spent countless hours at the eyepiece, sketching the dark markings on Mars and tracing what he believed to be the network of canals built by that imagined Martian civilization. His theories about Mars brought him fame and controversy in equal measure, for while the public was enchanted by the idea of intelligent life on another world, many of his fellow astronomers remained deeply skeptical, unable to see the canals that Lowell so confidently reported, and suspecting that what he observed was more the product of wishful thinking and optical illusion than objective reality. But Lowell was not a man to be easily discouraged by the doubts of others, and he continued his observations and his advocacy for the Martian canals until the end of his life, never abandoning the belief that had first drawn him to the stars. Yet Mars was not to be the only object of Lowell's astronomical obsession, for around the year 1905, his attention began to shift toward a new and perhaps even more tantalizing mystery, the question of whether there might exist another planet, a large and distant world lurking in the outer reaches of the solar system, beyond even the orbit of Neptune. The idea was not entirely new, of course, for astronomers had long suspected that the gravitational perturbations observed in the orbit of Uranus might not be entirely accounted for by Neptune alone, and there had been speculation, dating back to the mid-19th century, that yet another planet might be responsible for certain residual irregularities in the movements of the outer worlds. Lowell seized upon this idea with characteristic enthusiasm, and he set about attempting to calculate where such a planet might be found, applying his mathematical training to the complex problem of celestial mechanics. The work was painstaking and difficult, requiring Lowell to analyze decades of observations of Uranus and Neptune, searching for tiny discrepancies between their predicted positions and their actual observed locations, discrepancies that might betray the gravitational influence of an unseen body. He labored over these calculations for years, refining his methods and adjusting his assumptions, and gradually he developed a set of predictions for where this hypothetical ninth planet, which he called Planet X, might be located in the sky. In the year 1915, he published his findings in a work entitled Memoir on a Trans-Neptunian Planet, a detailed technical treatise in which he laid out his mathematical reasoning and identified several regions of the sky where he believed the planet was most likely to be found. The search for Planet X at Lowell Observatory employed the most modern techniques available to astronomers of that era, relying heavily upon photography rather than direct visual observation, for a large planet at the distance Lowell predicted would appear as nothing more than a faint point of light, indistinguishable from the countless stars that filled the photographic plates except for one crucial difference: it would move. The method was straightforward in principle, though exceedingly tedious in practice, for it required taking photographs of the same region of sky on different nights and then comparing them carefully to see if any of the countless points of light had shifted position relative to the background stars. A planet, being a member of our solar system, would orbit the Sun and thus would appear to drift slowly against the fixed backdrop of distant stars, and it was this motion that the searchers hoped to detect. The tool that made this comparison possible was the blink comparator, a device that allowed an observer to view two photographic plates in rapid alternation, switching back and forth between them so quickly that any object that had moved between the two exposures would appear to jump or blink, standing out from the stationary stars which remained fixed in place. The technique was effective but demanded great patience and sharp eyes, for each plate might contain hundreds of thousands of individual star images, and the observer had to examine every portion of the plate systematically, searching for that one telltale flicker that might indicate a moving object. The regions of sky that Lowell had identified as most promising lay near the plane of the Milky Way, where the density of background stars was greatest, making the work even more challenging, for there were simply so many stars to examine, and so many opportunities for a faint, slow-moving object to escape notice. And here we encounter one of those poignant ironies that seem to recur throughout the history of science, for unknown to anyone at the time, Lowell Observatory did in fact photograph the object that would eventually be identified as Pluto, not once but twice, in the year 1915, the very year that Lowell published his memoir predicting the existence of Planet X. The images were there, captured on the glass photographic plates, faint but real, but the tiny point of light that was Pluto was lost among the dense star fields of the Milky Way, overlooked by the searchers who did not recognize it for what it was. It is a melancholy thought, is it not, that Lowell came so close to finding the object he sought, that the evidence was literally in his hands, yet the discovery eluded him, hidden in plain sight among the multitude of stars. Percival Lowell did not live to see the search concluded, for he died in November of the year 1916, at the age of 61, his heart having given out after years of intense work and, perhaps, the accumulated strain of defending his unconventional ideas against persistent criticism. He was buried on the grounds of the observatory he had founded, on Mars Hill overlooking the town of Flagstaff, and there he remains to this day, beneath a small mausoleum designed to resemble the dome of a telescope, a fitting resting place for a man who had devoted so much of his life to studying the heavens. His death brought the search for Planet X to an abrupt halt, not only because the driving force behind the project was gone, but also because of a prolonged and rather unpleasant legal dispute that arose between the observatory and Lowell's widow, Constance. Constance Lowell, it seems, was dissatisfied with the provisions her husband had made for her in his will, and she contested the terms vigorously, initiating a legal battle that would drag on for nearly a decade and drain the observatory's resources, both financial and emotional. During this period, The institution that Percival Lowell had built was in a state of uncertainty, its future in doubt, and there was neither the money nor the energy to continue the systematic photographic search that had been underway before his death. The plates that had been taken sat in their storage cabinets, including those from 1915 that unknowingly contained images of Pluto, waiting for a time when the search might resume. It is worth noting that Lowell was not the only astronomer of his generation who had turned his attention to the possibility of a trans-Neptunian planet, for there existed a spirit of competition, a sense that the discovery of a new world would bring great prestige to whoever might achieve it first. Among the other searchers was William Pickering, an astronomer at Harvard who had himself made predictions about the location of a hypothetical planet O, as he called it, based on his own analysis of the orbital perturbations of the outer planets. Pickering's predictions differed somewhat from Lowell's, and the two men represented rival approaches to the same problem, each convinced that his own calculations were more likely to lead to success. The competition was not bitter or personal, by most accounts, but it added a certain urgency to the search, a sense that time was of the essence and that the prize might go to another if one did not move quickly enough. The methodology that both Lowell and Pickering employed was rooted in the same principles that had led to the discovery of Neptune decades earlier, the assumption that discrepancies in the observed positions of known planets could be explained by the gravitational influence of an undiscovered body, and that careful mathematical analysis could reveal where that body must be. But there was a crucial difficulty with this approach, one that would not become fully apparent until much later, which was that the residual perturbations in the orbit of Uranus that had motivated the search were actually quite small, perhaps even within the margin of error of the observations themselves, and the predictions that Lowell and others derived from them were correspondingly uncertain. They were searching, in a sense, for something that the data did not clearly require, and their confidence that they knew where to look was perhaps greater than the evidence warranted. Yet search they did, with dedication and persistence, taking plate after plate of the night sky, spending long hours at the blink comparator, hoping that the next image might reveal the prize they sought. The work was not glamorous. It was repetitive and tiring and often disappointing, but it was the kind of work that science frequently demands, the patient accumulation of observations, the methodical sifting through data, the willingness to continue even when results are slow in coming. And it was this tradition of careful, systematic searching, established by Lowell and continued by those who came after him, that would eventually lead to success, though not until more than a decade after Lowell's death, and not in quite the way he had imagined. The legal troubles with Constance Lowell were finally resolved in the mid-1920s, and the observatory was at last free to resume its work, to honor the memory of its founder by continuing the search he had begun. New equipment would be acquired, new staff would be hired, and the hunt for Planet X would begin again in earnest, with a young man from Kansas who had never attended university but who possessed sharp eyes and remarkable patience, and who would, in the fullness of time, find what Percival Lowell had so desperately sought. But that is a story for another section. And for now we may simply rest with the knowledge that the search had been initiated, the groundwork had been laid, and the discovery, when it came, would be the culmination of decades of effort by many hands, guided by the vision, however imperfect, of Percival Lowell. In the year 1906, On a small farm in the state of Illinois, a boy named Clyde William Tombaugh came into the world, born to a family of modest means and practical sensibilities, people who worked the land and understood the rhythms of planting and harvest, of seasons turning slowly one into another. His father, Murin Tombaugh, was a farmer, as were most men in that part of the country, and his mother, Adela, kept the household running with the quiet efficiency that farm life demanded. There was nothing in the circumstances of his birth that might have suggested young Clyde would one day make a discovery that would capture the imagination of the entire world, that his name would become forever linked with the cold and distant reaches of the solar system. But perhaps that is often the way with those who achieve remarkable things, that they begin in the most unremarkable of settings, their futures as yet unwritten and full of quiet possibility. When Clyde was still a young boy, his family moved from Illinois to Kansas, settling on farmland where the skies stretched wide and unobstructed from horizon to horizon, where on clear nights the stars appeared in such profusion that they seemed almost crowded together, the Milky Way a soft and luminous band arching overhead. It was beneath these Kansas skies that the young Tombaugh first developed his fascination with astronomy, lying on his back in the fields after the day's work was done, watching the stars wheel slowly overhead and wondering about the nature of those distant points of light. His uncle had a small telescope, a modest instrument by any standard, but to young Clyde it was a window into another world entirely, a means of reaching out across the vast emptiness of space to touch, if only with his eyes, the surfaces of other worlds. The Tombaugh family did not have money for expensive scientific equipment, but what Clyde lacked in financial resources, he more than made up for in determination and ingenuity. He began to teach himself the principles of telescope construction, reading whatever books and articles he could find on the subject, studying the mathematics of mirror grinding and the physics of light. He obtained old pieces of farm machinery, a crankshaft from a discarded 1910 Bic, parts from a cream separator that had seen better days, and from these humble materials he began to fashion his own telescopes. There is something rather lovely about this image, the young man working in a shed or barn, surrounded by the detritus of agricultural life, carefully grinding and polishing mirrors that would allow him to see the rings of Saturn or the moons of Jupiter. He built not one telescope but several, each more sophisticated than the last, teaching himself through trial and error, through patient experimentation, the craft of the amateur astronomer. By the time he was in his early 20s, Clyde Tombaugh had become quite accomplished in his self-taught discipline. He made detailed drawings of the planets as they appeared through his homemade telescopes, careful renderings of Mars and Jupiter that showed not merely artistic skill but genuine observational acuity. In 1928, at the age of 22, he made a decision that would alter the course of his life entirely. He gathered up his best drawings, his careful sketches of planetary surfaces, and sent them to the Lowell Observatory in Flagstaff, Arizona, hoping perhaps for some feedback, some acknowledgement from professional astronomers that his work had merit. What he received in return was something far more significant, an offer of employment that must have seemed almost miraculous to a young man from a Kansas farm with no formal training in astronomy. The Lowell Observatory had been founded by Percival Lowell in 1894, and though Lowell himself had died in 1916, his legacy continued to shape the institution's research priorities. Lowell had been convinced that a ninth planet existed beyond the orbit of Neptune, and the observatory that bore his name remained committed to finding it. The search had languished somewhat in the years following Lowell's death, but by the late 1920s the observatory's director, Vesto Melvin Slipher, had decided to renew the effort. A new photographic telescope had been acquired specifically for this purpose, and what was needed now was someone to operate it, someone to take the photographs and examine them with the patience and care the task demanded. When Slipher received young Tombaugh's drawings, he recognized in them the work of someone with precisely the qualities required: sharp eyes, steady hands, and the temperament for detailed, meticulous observation. And so in January of 1929, Clyde Tombaugh arrived at the Lowell Observatory, a young man of 22 with no university degree, no formal credentials, only his self-taught skills and his determination to prove himself worthy of the opportunity he had been given. Vesto Slipher explained to him the nature of the work ahead, the systematic photographic survey of the night sky that would, they hoped, reveal the planet that Percival Lowell had spent so many years searching for. The method was straightforward in principle but extraordinarily demanding in practice. Photographs would be taken of particular regions of the sky on different nights, and these photographs would then be compared to see if any object had moved relative to the fixed stars. A planet, being much closer than the stars, would shift its position noticeably over the course of even a few days, and this movement would betray its presence among the countless points of light that filled each photographic plate. The instrument used for this comparison was called a blink comparator, a device that allowed the observer to switch rapidly back and forth between two photographic plates of the same region of sky, taken on different dates. If everything in the field of view was a distant star, the two images would appear identical, and the blinking would produce no apparent change. But if something had moved between the two exposures, it would appear to jump back and forth as the observer switched between plates, drawing the eye to its position among the stationary stars. The principle was elegant, but the execution was grueling, for each photographic plate might contain as many as 400,000 individual stars, tiny points of light that had to be examined one by one, region by region, the observer searching for that single telltale jump that would indicate something worthy of further investigation. Tombaugh threw himself into this work with a dedication that bordered on the obsessive. Night after night he operated the telescope, guiding it carefully to keep the stars fixed in position during exposures that might last for an hour or more. Day after day he sat at the blink comparator, his eyes moving methodically across the paired plates, searching, always searching, for that tiny anomaly that would reward his efforts. The work was tedious beyond description, the kind of task that might have driven a less patient person to distraction, but Tombaugh understood that great discoveries often emerge from just such unglamorous labor, that the universe does not yield its secrets easily but must be coaxed and pursued with relentless persistence. Months passed in this fashion, with Tombaugh taking photographs and examining them, finding nothing of significance, then taking more photographs and examining those as well. The work continued through the summer and autumn of 1929, through the winter holidays and into the new year. By January of 1930, Tombaugh had refined his technique considerably, had learned to recognize at a glance the various phenomena that might produce false alarms, the variable stars that brightened and dimmed, the asteroids that wandered through the field of view, the tiny flaws in the photographic emulsion that might be mistaken for celestial objects. He had become, through sheer practice and determination, an expert at this particular form of astronomical detection. On the night of January 23, 1930, Tombaugh trained the telescope on a region of the sky in the constellation Gemini, taking a careful photograph of the star field there. 6 nights later, on January 29, he photographed the same region again, obtaining a second plate that would be compared with the first using the blink comparator. The 2 plates were then set aside while Tombaugh continued with other observations, other comparisons, the methodical work of the survey proceeding as it always did, one small step at a time. It was on the afternoon of February 18, 1930, that Clyde Tombaugh sat down at the blink comparator to examine the plates from Gemini. He had no particular expectation that this session would be different from any other, no premonition that he was about to make the discovery of a lifetime. He simply began his work as he always did, scanning systematically across the paired images, watching for anything that might jump or shift as he switched between plates. And then, at approximately 4 o'clock in the afternoon, something did jump. A tiny point of light, barely visible among the multitude of stars, shifted its position unmistakably as the images alternated. Tombaugh checked and rechecked what he was seeing, making certain that this was not an artifact or an asteroid or any of the other phenomena he had learned to recognize. The object was faint, perhaps of the 15th magnitude, far dimmer than any of the known planets, but its movement was real and could not be explained away. In that moment, alone at the blink comparator in the quiet of the observatory, Clyde Tombaugh knew that he had found something significant. He did not rush to make an announcement, did not call out to his colleagues in excitement, but instead continued to examine the plates with the same careful methodology that had characterized all his work. He found a third plate, taken on January 21, and located the object there as well, confirming that its motion was consistent with what would be expected of a distant planet. Only then did he walk down the corridor to the office of Vesto Slipher and inform him, in calm and measured tones, that he believed he had found Lowell's planet. What followed was a period of careful verification that stretched over several weeks. The observatory staff knew that any announcement of such a discovery would be met with intense scrutiny from the astronomical community, and they were determined to be absolutely certain of their findings before making them public. Additional photographs were taken, the object's position was tracked over time, its motion was calculated and compared with the theoretical predictions that had guided the search. Everything was consistent with a planet located in the outer reaches of the solar system, far beyond the orbit of Neptune, moving slowly through the star field as it pursued its long and lonely orbit around the Sun. The announcement was finally made on March 13, 1930, a date that had been chosen with considerable care. It was the 149th anniversary of William Herschel's discovery of Uranus, and it was also the 75th anniversary of Percival Lowell's birth. The coincidence of these dates seemed fitting, a way of honoring the traditions of planetary discovery while also paying tribute to the man whose vision had initiated the search. Clyde Tombaugh, the farm boy from Kansas who had built telescopes from automobile parts and cream separators, had achieved what Percival Lowell himself had never managed in his lifetime: the discovery of the 9th planet of our solar system. The question of what to name this new world generated considerable discussion both within the astronomical community and among the general public. Various suggestions were put forward, including Minerva, the Roman goddess of wisdom, and Cronus, the Greek god who was father to Zeus and ruler of the Titans. But the name that ultimately prevailed came from a rather unexpected source: an 11-year-old girl in Oxford, England, named Venetia Burney, who suggested to her grandfather over breakfast one morning that the new planet might be called Pluto, after the Roman god of the underworld. Her grandfather, Falconer Muddon, happened to be a retired librarian with connections to the astronomical community, and he passed the suggestion along to Herbert Hall Turner, a professor of astronomy at Oxford, who in turn communicated it to the Lowell Observatory. The name Pluto appealed to the observatory staff for several reasons. It was mythologically appropriate, referring to a god of the dark and distant realms, which seemed fitting for a planet so remote from the warming light of the sun. And the first two letters, P and L, happened to be the initials of Percival Lowell, allowing the name to serve as a subtle tribute to the man who had predicted the planet's existence and devoted so much of his life to searching for it. When the astronomical symbol for the new planet was designed, it took the form of a monogram combining these two letters, the P and the L intertwined in a symbol that would represent Pluto on charts and in calculations for decades to come. And so the discovery was complete, from the initial observation at the blink comparator to the announcement and the naming, a process that had unfolded over the course of several months with all the careful deliberation that characterized serious scientific work. Clyde Tombaugh would go on to have a long and distinguished career in astronomy, continuing to search the skies for other objects and contributing to our understanding of the solar system in many ways. But it is for the discovery of Pluto that he is best remembered, for those patient hours at the blink comparator, for the moment when a tiny point of light revealed itself to be something more than just another star, for the vindication of Percival Lowell's dream and the triumph of a self-taught astronomer from the plains of Kansas. The discovery of the outer planets, spanning nearly a century and a half from William Herschel's unexpected observation to Clyde Tombaugh's painstaking search, represents far more than the simple addition of new worlds to our cosmic inventory. These three discoveries, each accomplished through remarkably different methods and circumstances, fundamentally altered how astronomers understood the solar system and, perhaps more importantly, how they approached the very practice of astronomical investigation. The broader significance of finding Uranus, Neptune, and Pluto extends well beyond the objects themselves, touching upon questions of scientific methodology, the relationship between observation and theory, and the humbling recognition that our knowledge of even our own celestial neighborhood remains perpetually incomplete. When Herschel first noticed that peculiar greenish object through his homemade telescope on that March evening in 1781, he initiated what we might gently describe as a paradigm shift in astronomical thinking, though he himself would not have recognized it as such at the time. For thousands of years, the solar system had appeared complete and unchanging, bounded by Saturn's stately orbit, with 5 wandering planets visible to the unaided eye complementing Earth in a seemingly finished arrangement. The ancient astronomers had catalogued these worlds, the medieval scholars had contemplated their motions, and the early telescopic observers had refined measurements of their positions, all operating under the quiet assumption that no additional planets remained to be found. This assumption was so deeply embedded in astronomical consciousness that it rarely required explicit statement, functioning instead as an unexamined backdrop to celestial observation. Herschel's discovery shattered this assumption with gentle but irrevocable finality. The solar system, it turned out, was not the complete and bounded system that generations of astronomers had imagined, but rather an expanding frontier whose outer limits remained genuinely unknown. This realization carried profound implications for the practice of astronomy, suggesting that systematic observation might yet reveal entirely unexpected phenomena, that the universe held secrets invisible to casual inspection, and that the tools of patient, methodical investigation could extend human knowledge into previously unimagined territories. The discovery of Uranus demonstrated that novel objects of considerable significance could hide in plain sight within the familiar night sky, awaiting only the combination of adequate instruments, careful technique, and sustained attention to reveal themselves. This expansion of astronomical possibility encouraged a new generation of observers to search the heavens with renewed purpose, scanning the regions beyond Saturn's orbit for additional undiscovered worlds. The gap in the sequence of planetary distances, that curious void between Mars and Jupiter where mathematical relationships suggested a planet should reside, attracted particular attention, ultimately leading to the discovery of the first asteroids in the early years of the 19th century. Yet the most significant methodological development arising from Uranus's discovery would emerge not from extended telescopic searching but from the careful analysis of the new planet's orbital behavior, observations that would lead astronomy in an entirely unexpected direction. As decades of positional measurements accumulated, astronomers found themselves confronting an increasingly troubling discrepancy between Uranus's predicted positions and its actual location among the stars. The planet persistently refused to follow the orbital path calculated from Newtonian mechanics, drifting from its expected positions in ways that existing theory could not explain. This discrepancy posed a significant challenge to astronomical methodology, for if celestial mechanics could not accurately predict the motion of a known planet, the foundations of gravitational theory themselves might require revision. Some astronomers wondered whether Newton's laws, so successful in describing the motions of the inner planets and Saturn, might fail at the vast distances of the outer solar system, requiring modification or perhaps complete replacement. The resolution of this problem, achieved independently by Urbain Le Verrier in France and John Couch Adams in England during the 1840s, represented an unprecedented triumph of theoretical prediction in astronomical history. Rather than questioning the validity of Newtonian mechanics, these mathematicians proposed that Uranus's orbital irregularities arose from gravitational perturbations caused by an as yet undiscovered planet lying beyond Uranus's orbit. Working backwards from the observed discrepancies, they calculated where such a perturbing body must be located in order to produce the observed effects, effectively predicting the existence and position of a planet that no human eye had ever seen. When Johann Galle and Heinrich d'Arrest pointed the Berlin Observatory telescope toward Leverrier's predicted coordinates on that September evening in 1846 and found Neptune within 1 degree of the calculated position, they validated not merely a single prediction but an entire approach to astronomical discovery. The significance of Neptune's discovery for astronomical methodology can scarcely be overstated. For the first time in history, a major celestial body had been found not through direct observation but through mathematical deduction, not by scanning the heavens with telescopes but by performing calculations with pen and paper. This demonstration that theoretical analysis could lead observers to previously unknown objects established celestial mechanics as a tool of discovery rather than merely a means of describing known phenomena. The successful prediction of Neptune proved that the laws of physics, properly applied, could reveal the existence of things invisible to direct inspection, that the universe operated according to mathematical principles sufficiently reliable to guide the search for new worlds. This methodological transformation extended far beyond planetary astronomy, influencing how scientists in many fields approach the relationship between theory and observation. The aftermath of Neptune's discovery naturally inspired speculation about whether additional planets might lurk in the outer darkness, gravitationally influencing Neptune's orbit just as Neptune had perturbed Uranus. Among those captivated by this possibility was Percival Lowell, the wealthy American astronomer who dedicated the final years of his life to calculating the position of a hypothetical planet X and establishing an observatory in Arizona specifically to search for it. Lowell's calculations, based on perceived irregularities in Neptune's orbital motion, predicted where this trans-Neptunian planet should be found, and his observatory staff conducted extensive photographic searches until Lowell's death in 1916 and for many years thereafter. When Clyde Tombaugh finally identified Pluto in 1930, using the blink comparator to detect a faint point of light that shifted position between photographic plates taken several nights apart, the discovery appeared at first to represent another triumph of celestial mechanics prediction, another validation of the methodology that had succeeded so spectacularly with Neptune. The new planet lay reasonably close to the region where Lowell had predicted Planet X should be found, suggesting that mathematical analysis had once again guided observers to an undiscovered world. The discovery certainly demonstrated the effectiveness of systematic photographic survey techniques, showing that patient, methodical comparison of carefully obtained images could reveal objects too faint and slow-moving to be noticed through casual observation. However, subsequent investigation revealed an irony that continues to fascinate historians of science. As astronomers gathered more information about Pluto through the following decades, the new planet proved distressingly small and faint, far too diminutive to produce the gravitational perturbations that Lowell had attributed to Planet X. The irregularities in Neptune's orbit that had motivated Lowell's calculations turned out to be largely illusory, arising from small errors in the positional measurements available at the time rather than from the gravitational influence of an outer planet. Pluto's discovery, which had seemed at first to validate Lowell's predictions, was in fact essentially fortunate coincidence, a case of finding the right object in approximately the right place for largely the wrong reasons. This realization does not diminish the genuine achievement of Tombaugh's discovery, which required extraordinary patience, skill, and dedication over many months of demanding work. The systematic photographic survey technique that Tombaugh employed proved itself a powerful tool for detecting faint moving objects, a methodology that would later reveal countless asteroids, comets, and eventually other trans-Neptunian bodies. Yet the circumstances surrounding Pluto's discovery serve as a gentle reminder that scientific progress does not always follow the neat logical pathways that textbook accounts sometimes suggest, that chance and serendipity play their own roles in expanding human knowledge, and that being right for the wrong reasons remains a perfectly valid way of making important discoveries. The true nature of Pluto remained uncertain for nearly half a century after its discovery, with astronomers struggling to determine the size and mass of this distant, faint object. Early estimates suggested Pluto might be comparable to Earth in size, but these estimates steadily shrank as observational techniques improved, creating ongoing puzzlement about this peculiar world at the edge of the known solar system. The crucial breakthrough came in 1978, when James Christie at the United States Naval Observatory examined photographic images of Pluto and noticed that the planet's image appeared slightly elongated, not perfectly circular as a point-like object should appear. Careful analysis revealed that this elongation arose from the presence of a previously undetected moon, subsequently named Charon, orbiting so close to Pluto that ground-based telescopes could not fully resolve the two bodies as separate objects. The discovery of Charon proved transformative for understanding Pluto, because the orbital period and distance of a moon allows astronomers to calculate the mass of the planet it orbits, a straightforward application of Newtonian mechanics. When Christie and his colleagues performed this calculation, they found that Pluto's mass was far smaller than anyone had suspected, less than 1/5% of Earth's mass, making it by far the smallest object then classified as a planet. This revelation confirmed definitively that Pluto could not have caused the orbital perturbations Lowell had sought, for such a tiny body would exert negligible gravitational influence on Neptune's motion. The discovery also raised questions about whether such a small object truly deserved planetary status, questions that would simmer for decades before reaching formal resolution. The classification of Pluto became increasingly problematic as astronomers discovered that it was not alone in the outer solar system. Beginning in the early 1990s, observers began finding other icy bodies beyond Neptune's orbit, objects inhabiting a region that came to be known as the Kuiper Belt in honor of the astronomer Gerard Kuiper, who had theorized about such a population decades earlier. These trans-Neptunian objects, as they were formally designated, ranged widely in size, with most being considerably smaller than Pluto but a few approaching or even exceeding Pluto's dimensions. The discovery in 2005 of Eris, a scattered disk object larger than Pluto in some measurements, forced astronomers to confront a difficult choice. Either Eris and similar objects must also be classified as planets, potentially expanding the planetary population to dozens or hundreds of members, or Pluto must be reclassified to reflect its membership in a population of similar icy bodies. In 2006, the International Astronomical Union addressed this question by creating a formal definition of the term planet for the first time, establishing criteria that a planet must orbit the Sun, must have sufficient mass for its own gravity to pull it into a roughly spherical shape, and must have cleared the neighborhood around its orbit of other debris. Pluto meets the first two criteria but fails the third, sharing its orbital neighborhood with numerous other Kuiper belt objects of comparable size. The IAU therefore reclassified Pluto as a dwarf planet, a category that also includes Eris, Ceres in the asteroid belt, and several other bodies. This decision sparked considerable public discussion and some ongoing scientific debate, with certain astronomers arguing that the clearing criterion is inappropriate or that historical and cultural considerations should influence planetary classification. The exploration of these outer worlds has continued through robotic spacecraft that have ventured into the distant reaches of our solar system. Voyager 2, launched in 1977, conducted close flybys of Uranus in January 1986 and Neptune in August 1989, returning the first detailed images of these ice giant planets and their moons. These encounters revealed worlds of unexpected complexity, with Uranus's extreme axial tilt creating bizarre seasonal patterns and Neptune's atmosphere displaying remarkably active weather systems despite the weak sunlight reaching such distances. The New Horizons spacecraft, launched in 2006 and arriving at Pluto in July 2015, transformed our understanding of this distant world, revealing a geologically diverse surface with nitrogen ice glacier, water ice mountains, and a thin atmosphere that expands and contracts as Pluto moves along its elliptical orbit. The discovery of the outer planets thus opened questions that continue to guide astronomical investigation today, questions about the extent and contents of our solar system, about the processes that shaped these distant worlds, and about what other objects might await discovery in the vast darkness beyond Neptune's orbit. From Herschel's unexpected observation through Tombaugh's patient search to the robotic explorers now venturing into the outer solar system, the story of the outer planets demonstrates how each discovery expands not only what we know but also what we recognize we do not yet know, gently reminding us that the universe remains larger and more varied than any single generation can fully comprehend.